The agenda for today is to first cover the technical details behind cross-site scripting vulnerabilities. So what is a cross-site scripting vulnerability? What are the different types of cross-site scripting vulnerabilities? How common and critical are these types of vulnerabilities? And so on. Next, we're going to cover how to find and exploit XSS vulnerabilities. So imagine you've been given an application and asked to test it. How would you go about testing the application to determine if it's vulnerable? In this section, we'll go over XSS vulnerabilities of varying difficulty levels and how to exploit them. And we'll even discuss how to bypass certain defenses that are put in place by developers. Last but not least, we'll cover the different techniques that can be used to prevent or mitigate cross-site scripting vulnerabilities. Alright, so far we've learned the theory behind cross-site scripting vulnerabilities, and we looked at the three different types of XSS vulnerabilities. In this section, we're going to discuss how to find and exploit these types of vulnerabilities. Finding and exploiting XSS vulnerabilities varies slightly depending on the type of cross-site scripting vulnerability. So the way we're going to approach this section is we're going to discuss it based on each type, and we'll start off with reflected cross-site scripting vulnerabilities. The first thing that you want to do is identify every endpoint in the application where user-supplied data is reflected in the response. This includes parameters or other data within the URL query string, the URL file path, and even in some cases, HTTP headers. Now, the way you would do that is you would submit a unique arbitrary string that does not appear anywhere in the application and is unlikely to be affected by XSS-specific filters. The reason we do that is because we want to query the responses in the application to see if our unique string appears in them. An example string would be, let's say, test12564, which I just came up with. It's just a short string of alphanumeric characters, and it does not contain any tag names or special characters, and so it's quite unlikely to be blocked by any XSS filters that the application uses. Now, once you've entered this string in every endpoint of the application, then it's a matter of monitoring the application's responses for the appearance of that string. When you do find it in the response, that means you have found a location in the application where client-supplied input is reflected in the application. That in itself does not mean that it's vulnerable to XSS. However, it does mean that it definitely needs to be tested for reflected cross-site scripting vulnerabilities. So the next step would be to determine the reflection context. That's the syntactic context in which the data is reflected. So for example, is it reflected in a tag attribute, or maybe it's reflected in a script element, or even an attribute containing a URL? Depending on where it's reflected, the payload will be different. So it's important to understand the payload context, and then based on that, test your candidate payloads. We'll have a few examples in the next couple of slides that go over a few different contexts, and then based on those contexts, we'll build our payloads. Now, when you're testing your candidate payloads, chances are you're doing that using a tool like Burp Repeater. So it's always a good idea that when you do see your payload reflected and potentially vulnerable, you always should go back and test it in the browser to make sure that it is truly vulnerable. All right, let's look at a few reflected contexts and how you would build your payload based on each specific context. In the first example over here, the unique test string gets reflected in the value attribute of the input element. So you could see over here, this is my test string, which is test12564, and it's getting reflected in the value attribute of the input element. So in order for me to exploit this XSS vulnerability, I need a way to get out of the value attribute and even potentially get out of the input tag so that I could add my own malicious script. So the first payload that you could potentially use is the one in red right over here. The first thing that we're doing is adding a double quote so that we could close off the double quote for the string right over here. And then we're adding an angle bracket so that we could get out of the input element. And then it's just a matter of adding our malicious script, which just alerts a user with the integer 1. Note over here, we do have a trailing double quote and an angle bracket, which comes from right over here. But that's okay because the browser does its best to render a page, even if there are some errors in the code. And so this is not going to break the application. So that's the first way you could exploit the vulnerability. Another payload you could use is the onFocus event, which gets triggered when you focus or click on an input element. In this case, you add a double quote again to close off this string right over here, but you stay in the input tag and you just add an onFocus event to run your malicious code. Note over here that we no longer have a trailing double quote and an angle bracket, so it's a cleaner payload, but it does require some user interaction in order for it to be triggered. So my preference would go to payload number 1. Another example is that your unique string is directly inserted in a quoted string within an existing script. So if you look over here, our string got inputted in some variable called a. So the way you would exploit that is to first close off the string using a single quote right over here. And then we add our own semicolon to end the initiation of that variable. And then we simply add our malicious code because we're already running in a script tag. And then we add a new variable called faux, which doesn't really do anything. It's just used so that we could close off the single quote that comes from over here to make sure that you don't introduce any errors that could potentially cause the script to run. Another example is the unique string gets added as part of the href attribute, which specifies the URL of the page. So you could see over here, my URL string is part of the href attribute. The way you would exploit that is use the JavaScript protocol to introduce the script directly within the URL attribute. Another way you could also exploit it is to simply get out of the href element by using the hash sign, which just denotes a page fragment and doesn't really go anywhere. And then you add the onClick event to run your malicious code. And that's essentially it. So with the 3 examples that we saw, each reflected context required a different payload. And so it's really important to understand the context in which your input is reflected before you start throwing random payloads at an input vector. Now, I do want to bring your attention to an amazing resource that is provided by the Portswigger organization. It's called the Cross-Site Scripting Cheat Sheet, and it essentially gives you all the different tags that you could potentially use and all the different event handlers that you could potentially use to create XSS payloads. And when you do select, let's say, a specific tag, it gives you the list of the payloads that you could use for that specific tag, and then it also tells you which browsers that payload would work on. It's an amazing resource that you'll see me use extensively in the lab videos, so I definitely recommend that you check it out, and I added the link on the screen right over here. I also have the link in the resources section. One thing that you might come across when pen testing applications is that there are certain filters or defense mechanisms that are put in place by developers to prevent cross-site scripting attacks. Now, depending on the defense that is put in place, you might be able to bypass it. So, for example, a certain defense would be that specific tags and even event handlers are blocked. In that case, the way you would approach it is you would use the XSS cheat sheet, which we just talked about in the previous slide, and run a brute force attack to determine which tags are allowed first, and then based on that specific tag, which event handlers are allowed and not blocked by the application. Another defense mechanism could be, let's say, no quotes of any kind are allowed in the input vector. In that case, you could use the fromCar code function to return a string that is created from a sequence of UTF-16 code units. Over here, you could see that I'm just saying the word XSS, but in a real payload, it would be much bigger than that. But this allows you to bypass the fact that you need to use single quotes or double quotes. Another filter could be specific strings are not allowed. This can sometimes be bypassed by adding white spaces to break up keywords. This works because browsers can be a little bit lenient when it comes to white spaces in HTML and JavaScript. And so let's say the string JavaScript is not allowed. What you could do is simply add a tab in between the word to break up the word, and therefore it does not get picked up by the filter in the application. You could even use the encoded version of a tab. There's a ton more defense mechanism techniques that you could apply depending on how the application that you're testing functions. I've added a link to the OWASP XSS filter evasion cheat sheet if you're interested in learning more about the different evasion techniques. All right, we spent quite some time on how to find and exploit reflected XSS vulnerabilities, and that's okay because everything that we learned for reflected XSS vulnerabilities applies for finding stored XSS vulnerabilities. So the first step is the same. You need to identify every endpoint in the application where data is reflected in the response of the user. This again includes parameters in the URL, in the message body, in HTTP headers, and so on. Once you identify all the input vectors, you submit a unique arbitrary string that is not likely to be blocked by XSS filters. So again, we use the example of the string test12564. Now, the difference over here between stored XSS and reflected XSS is that with stored XSS vulnerabilities, the data entered in one location may be displayed in many locations in the application, which makes it a bit more cumbersome to find. So you would need to review all the application's content and functionality to identify any instances where the unique string is displayed back in the browser versus just reflected in the response of the exact request where you put the string. Now, once you do identify the instances, the steps are the same. You first need to determine the context, test candidate payloads in your proxy, and then confirm the attack in your browser. So everything that we learned for how to exploit reflected XSS vulnerabilities applies. It's just that the data is not directly reflected in the same response of the request. It might be reflected in multiple locations in the application. Okay, moving on to finding and exploiting DOM-based XSS vulnerabilities. This type of vulnerability is a bit harder to find. Since DOM-based XSS vulnerabilities occur when JavaScript is taking in client-supplied input and passing it to a sink, or what we said, a potentially dangerous function, then the first step would be to review every piece of client-side JavaScript and identify instances where you have sinks or potentially dangerous functions that are used to access DOM data and can be controlled using client-supplied input. So example sinks would be document.write or document.writeLine or document.domain or element.inner HTML and so on. Now, once you identify the source that leads to a sink, then you add your unique arbitrary string and use the browser's developer tools to follow the path of execution to the sink. And then once you understand the path of execution, it's really just a matter of building your payload and testing it in the browser. In the upcoming videos, we'll be going over 30 labs that give you plenty of hands-on experience exploiting all three types of cross-site scripting vulnerabilities. So if you still feel like you don't understand a specific type of XSS or certain variations of a specific type of XSS, don't worry, you'll get plenty of hands-on experience when you actually exploit vulnerabilities in the lab environment. Of course, we can't end this section without mentioning web application vulnerability scanners, which are essentially automated tools that crawl your web application and look for vulnerabilities. I would say any decent scanner should have the ability to identify most reflected cross-site scripting vulnerabilities, just because the way you find them is a little bit easier than stored or DOM-based XSS vulnerabilities. Now, for stored or DOM-based XSS vulnerabilities, like I said, they're a bit harder to find, and so some scanners will report them, whereas others might miss them. So it's always a good idea to run a scan and then also perform a manual check to confirm that the scanner didn't miss anything. I personally use Burp Suite Pro Scanner, but there are so many other options ranging from open source to very expensive. So really, it's whatever you're comfortable with and whatever you're used to, and also the budget that the organization has to purchase such a scanner. All right, in the past couple of slides, we learned the technical details behind cross-site scripting vulnerabilities. We looked at the different types of XSS vulnerabilities, and then we learned how to find and exploit these types of vulnerabilities. In this section, we're going to discuss how to prevent or mitigate XSS vulnerabilities. The first and official defense to preventing cross-site scripting vulnerabilities is to encode any user-controllable data on output before it's displayed on the page. This ensures the user-supplied input is displayed safely as data versus as part of the client-side code. Now, this type of encoding you do is context-dependent. So depending on the technologies that you're using, you may need to apply multiple combinations of different encoding schemes. Let's say you're inserting client-supplied input within HTML, then you will need HTML encoding. Whereas if you're inserting client-supplied input within JavaScript, then you need JavaScript encoding. So it really depends on the technologies that you're using and what this client-supplied input is interacting with. Now, just like with encryption algorithms, it's not recommended that you implement your own encoding library. And that's because chances are you're going to end up missing something and leave your application vulnerable to cross-site scripting vulnerabilities. So you really should always use an existing well-known library for the encoding mechanisms that you need and for the technologies that you're using. So if you go to the OWASP website, you'll see that there's a ton of libraries that are recommended depending on the languages that you're using for your application or the frameworks that you're using. Next, filter or validate input on arrival. This involves only accepting input based on what is expected or valid. For example, if you have an age field, then you should have a check in the backend that only accepts integers for that field. You definitely shouldn't be accepting alphabets. You should also not be accepting any other type of characters. Of course, when it comes to filtering input, using an allow list or a whitelist is much more secure than using a blacklist or a deny list. However, there will be situations where you're forced to use a deny list, and that's why filtering input on arrival is actually considered a defense in depth versus a complete defense against cross-site scripting vulnerabilities. Another defense in depth that you could perform is using the appropriate response headers. The content type and the X content type options headers indicate the format of the responses of your requests. So if you set them appropriately, an attacker would not be able to inject HTML or JavaScript in pages that don't have that specific format or what's also called as that specific mem type. Of course, this does not work on all pages because some pages do need to have HTML and JavaScript in them, and that's why this is also considered to be a defense in depth versus the official defense when it comes to preventing cross-site scripting vulnerabilities. Last but not least, you could use content security policy as a last line of defense. Content security policy is a browser security mechanism that restricts the resources that a page can load and restricts whether a page can be framed by other pages. So this helps in mitigating vulnerabilities like cross-site scripting vulnerabilities and clickjacking vulnerabilities. The way it works is that you set a response header called the content security policy header, and it contains one or more directives separated by semicolons, defining the policies and restrictions that you've set. In the example that we have set over here on the screen, the policy allows images, it allows scripts, AJAX, and CSS from the same origin and does not allow any other resources to load. So let's say if you're an attacker and you're loading a script from your attacker-controlled server, the content security policy header would not allow it because it's not coming from the same domain of the application. Of course, the setting that we have on the screen is a very strict configuration and it can be loosened up a bit based on your needs. I've got a link in the resources section that explains everything that you need to know about the content security policy. I definitely recommend that you check it out because this is a whole topic on its own that could take a full hour to explain, and we're not going to do that in this module. We do, however, have a few labs that involve the content security policy, so when it comes to XSS prevention. So the things that you absolutely should be doing is encoding any user controllable data on output and filtering input on arrival. But as defense in-depth mechanisms, you could also use the appropriate response headers to restrict the format of your responses, and then you could also use the content security policy header to restrict where scripts, images, and resources are loaded from in the application. Hi everyone, welcome back to another video in the Web Security Academy series. In today's video, we'll be covering lab number 1 in the XSS module, titled Reflected XSS into HTML Context with Nothing Encoded. If you do not have an account on the Web Security Academy, you can get one by visiting the URL portsfigure.net/websecurity and clicking on the sign up button. I already have an account and I am logged in, so to access the exercise, I'm going to click on Academy, select all labs, do a search on cross-site scripting labs and select lab number 1 titled Reflected XSS into HTML Context with Nothing Encoded. Alright, let's get started. This lab contains a simple reflected cross-site scripting vulnerability in the search functionality. To solve the lab, perform a cross-site scripting attack that calls the alert function. So the target goal over here is to exploit the reflected cross-site scripting vulnerability in the search functionality in order to call the alert function. Alright, let's access the lab. Now notice over here, this is the built-in browser in Burp, and so all my requests are already being passed in my Burp proxy. So when it comes to cross-site scripting, the first thing we're looking for is input that gets stored or reflected back to the user in the application. So you could see over here, there's a search functionality. If we put in any string in the search functionality and click on search, you could see that the search string that we inputted gets reflected back to the user, and so this definitely should be tested for cross-site scripting. Now, if we go back over here, and let's send this to repeater, hit send, and look for our string test, you could see that it's only reflected in one location, which is in the heading over here. So this field over here needs to be tested for cross-site scripting. And before we put our payload, what we'll do is we'll just put in a classic character that is usually used for cross-site scripting and see if it's encoded. So we've hit search right over here. And if we go back to proxy, this was the request. And let's see if this request, so we're looking for search results. And here we go. So you could see over here, the less than sign is not encoded on output. And so this is definitely vulnerable to cross-site scripting attacks. So let's create our payload over here. In order to complete the exercise, we need to call the alert function. So we'll say script alert1 and then end our script tag. All this does is essentially present us with a new window, so an alert box that displays the content of the string that is inputted in the alert function, which in this case is just 1. So let's hit search right over here. And here we go. So we get an alert box with the string that we inputted in the alert function, which means that the string that we put in the search field was interpreted as part of the client-side code. So as JavaScript, which means that we've exploited the cross-site scripting vulnerability. So if we hit OK right over here, we should see the congratulations, you solved the lab message. So let's reload again. And here we go. We get the congratulations, you solved the lab message. All right, so we successfully completed the exercise by exploiting the reflected cross-site scripting vulnerability. In the next lab, we'll look at another case of an XSS vulnerability. Hi everyone, welcome back to another video in the Web Security Academy series. In today's video, we'll be covering lab number 2 in the cross-site scripting module titled Stored XSS into HTML Context with Nothing Encoded. If you do not have an account on the Web Security Academy, you can get one by visiting the URL portsfigure.net/websecurity and clicking on the sign up button. I already have an account and I am logged in, so to access the exercise, I'm going to click on Academy. Select all labs, do a search on cross-site scripting labs, and select lab number 2 titled Stored XSS into HTML Context with Nothing Encoded. Alright, let's get started. This lab contains a stored cross-site scripting vulnerability in the comment functionality. To solve this lab, submit a comment that calls the alert function when the blog post is viewed. So the target goal over here is to exploit the stored cross-site scripting vulnerability in the comment functionality and call the alert function. Okay, let's access the lab. Now notice over here, this is the built-in browser in Burp, and so all my requests are already being passed in my Burp proxy. All right, so for cross-site scripting vulnerabilities, what we're looking for is client-supplied input that is reflected or stored in the application and then reflected back to the user. So if we click on View Post right over here, you could see that you're allowed to add comments to the post, and the comments get displayed back to you under the post. And so over here, if the application does not properly validate input and encode it on output, then it could potentially be vulnerable to a stored cross-site scripting vulnerability. And this is much worse than a reflected one because all you have to do is enter your XSS exploit in whatever field that is vulnerable, and then anyone that visits this post over here, that XSS exploit will run in their browser, and then depending on what malicious action that XSS exploit does, it could have severe impact on the entire application itself. And so with reflected XSS, you would have to send a phishing link to a user, but with stored XSS, all you have to do is put it in the application. It gets stored, and anyone that visits this post, it will execute for the user. So the first thing we're going to do is see if the comment functionality is vulnerable. So we'll enter proper input first and see which ones are reflected back to us. So let's say test@test.ca, and then the website will say http test.ca, post comment, and then we'll visit the blog again. And you could see our comment is entered over here. So we've got the comment field is reflected back to us, and then the name field is reflected back to us. Also, the href element, so the link that we put for the website, could also potentially be vulnerable to cross-site scripting. So we'll start off with testing the comment field and see if it's vulnerable. So we'll add our classic cross-site scripting payload, script alert1, and then we'll close this script tag. All this does is call the alert function, which outputs a window that contains the string that is inputted in the alert function, which in this case is just 1. So let's put test and then test@test.ca, and then let's say the website is http www.test.ca. Now, if the input is properly encoded and validated in the backend, what happens is that this is viewed as a literal string instead of as part of the client-side code. If we do get an alert, that means it is interacting with the JavaScript and it is being viewed as JavaScript, and therefore it calls the alert function. So let's click on post comment. And we already get the congratulations, you solved the lab message, and so we know that we've successfully exploited the XSS vulnerability. But if we go back to the blog, we should see an alert box, and we do. So you can see over here, there's an alert box that contains our string. Click OK. If you go back over here, notice that the comment is not even displayed because it is seen as part of the client-side code, and so it was executed as client-side code. And we could see that in the response of the request over here. So if we look for the alert function, you could see that it's literally viewed as client-side code instead of as a string, and therefore the application is vulnerable to an XSS vulnerability. All right, so we successfully completed the exercise by exploiting the stored XSS vulnerability. In the next lab, we'll look at another case of a cross-site scripting vulnerability. Hi everyone, welcome back to another video in the Web Security Academy series. In today's video, we'll be covering lab number 3 in the cross-site scripting module titled DOM XSS in document.write_sync using source location.search. If you do not have an account on the Web Security Academy, you can get one by visiting the URL portsfigure.net/websecurity and clicking on the sign up button. I already have an account and I am logged in, so to access the exercise, I'm going to click on Academy, select all labs, do a search on cross-site scripting labs, and go to lab number 3 titled DOM XSS in document.write_sync using source location.search. All right, let's get started. This lab contains a DOM-based cross-site scripting vulnerability in the search query tracking functionality. It uses the JavaScript document.write function, which writes data out to the page. The document.write function is called with the data from location.search, which you can control using the website URL. To solve this lab, perform a cross-site scripting attack that calls the alert function. All right, so the target goal over here is to exploit the DOM-based XSS vulnerability and call the alert function. Okay, let's access the lab. Now notice over here, this is the built-in browser in burp, and so all my requests are already being passed in my burp proxy. When it comes to DOM-based XSS vulnerabilities, I don't really like using the proxy. Instead, what I do is I use the developer tools in the browser itself to understand exactly where my input is going. And so for today, we won't really be using the proxy. All right, the first thing that I do is map the application and see if any of the parameters could potentially be vulnerable to XSS. The way to do that is by putting in a string in the parameter and see if it's reflected back to the user or potentially even interacting with the document object model, or what we call in short, the DOM. So you could see over here we've got a search functionality. What I'm going to do is put in a unique string, so a random string. Let's say 1, 2, 3, 4, 5, 6, and click on search. Now you could see over here, it is reflected back to the user, and so this definitely needs to be tested for cross-site scripting vulnerabilities. And the way we're going to see if it's actually vulnerable is again by using the developer tools in the browser. So right click and then inspect, and then over here I'm going to do a Control F to search for my string. So 1, 2, 3, 4, 5, 6, and you could see we've got 2 matches for the string. The first one is the heading element where it's reflected back to the user. This should be tested for reflected cross-site scripting. But then there's also another match on my string. So if we enter again, you could see that my string made it into this URL over here, which is interesting. So we've got resources/images/tracker.gif or GIF, whatever way you say it. And then we've got search terms is equal to the string that I put into this parameter right over here. So I'm wondering how this got generated, because if it got generated in an unsafe way, it could potentially be vulnerable to DOM-based XSS. So to do that, I'm just going to right click and view the page source to see if there's any JavaScript which generates this link right over here. So if we go right over here and search for search term, and here we go. So this is the JavaScript that is responsible for generating that URL. And if we just scroll to the right, you could see all it does is it takes the search parameter from the request itself, so whatever we put into this parameter right over here, and then it saves it in a variable called query. And if query is not empty, so if someone put in a string in that search parameter, it calls the function track search and gives it the string that we inputted in the search parameter. Now in track search over here, which is this function, it writes to the page using document.write saying create an image that has the source /resources/images/tracker.gif. Search terms is equal to the string that we put in the search parameter. Okay, so this could potentially be vulnerable to DOM-based XSS because, as you could see over here, this is client-supplied input that makes changes to the document object model. So it's making changes to the page, and it's client-supplied input. And so we should be able to break out of this string right over here and get the application to perform an action on our behalf. So let's copy this whole thing over here. So this is what it's doing. So it's creating this image tag right over here. And then you could see the image tag right over here. All right, so the idea is that when we put in 1, 2, 3, 4, 5, 6, as you saw over here, it replaced it in the query string and it became 1, 2, 3, 4, 5, 6. So what we want to do is break out of this image tag and then add our malicious cross-site scripting payload. So to do that, the first thing we need to add is a double quote so that we could close this double quote right over here. And then we need to close the tag for the image element. So we'll do that. And then we could enter any script tag that we want or any malicious XSS payload that we want. So in this case, the lab tells us that all we need to do is alert on something. And so we'll use the script tag to call the alert function. And that is it. So let's copy this. This over here would be our payload. You don't actually need to put in an integer because it'll just be empty. So we'll copy this, put it in here. And so now when I search, what should happen is it should create the image tag with an empty search term, but it also should create a script tag that automatically runs when the page is loaded that alerts on the number 1. So let's search over here. And here we go. We got alerted. Let's click OK. And you could see we get the message, congratulations, you solved the lab. All right, so if we go back right over here and we search for this string over here, so you could see the leftover double quote and the bigger than or equal sign that were left over from this image tag over here. You could see them on the page. So we're just going to search for them and see how we ended up performing our exploit. And here we go. So you could see over here, this is the image tag that takes in whatever string that is put in the search field right over here. We were able to close that string and then close the image tag and then add our own malicious JavaScript that alerted the user. And that's essentially it. All right, so we successfully completed the exercise by exploiting the DOM-based XSS vulnerability. In the next lab, we'll look at another case of a cross-site scripting vulnerability. Hi everyone, welcome back to another video in the Web Security Academy series. In today's video, we'll be covering lab number 4 in the cross-site scripting module titled DOM XSS in inner HTML sync using source location.search. If you do not have an account on the Web Security Academy, you can get one by visiting the URL portsugar.net/websecurity and clicking on the sign up button. I already have an account and I am logged in, so to access the exercise, I'm going to click on Academy. Select all labs, do a search on cross-site scripting labs and select lab number 4 titled DOM XSS in inner HTML sync using source location.search. All right, let's get started. This lab contains a DOM-based cross-site scripting vulnerability in the search block functionality. It uses an inner HTML assignment, which changes the HTML content of a div element using data from location.search. To solve the lab, perform a cross-site scripting attack that calls the alert function. All right, so our target goal over here is to exploit the DOM-based XSS vulnerability to call the alert function. Let's access the lab. Now notice over here, this is the built-in browser in Burp, and so all my requests are already being passed in my Burp proxy. When it comes to DOM-based XSS vulnerabilities, I don't really use the proxy. Instead, I use the developer tools in the browser to understand exactly where my input is going. And so for this lab, we won't be using the proxy, and instead we'll just be using the browser. Now, as usual, the first thing to do is map the application and see if any of the parameters could potentially be vulnerable to XSS. The way to do that is by putting in a string in the parameter that you think might be vulnerable and seeing if it's reflected back to the user or potentially even interacting with the document object model. So what we're going to do over here is just enter a unique random string. So let's say 1, 2, 3, 4, 5, 6 and click on search right over here. Notice that it is reflected back to us right over here. So we're going to right click and inspect to see if there's any other locations in the application where it's reflected. So under the Elements tab over here, let's do Control Find and then search for our string. Now notice over here, there's only one location in the application where it's reflected to us, which is the search message span element. Now what I'm going to do is I'm going to view the page source to see if there's any JavaScript that is generating this span element over here. So let's right click and view page source. And right away I could see that there is JavaScript and it looks like it is what is responsible for populating the search message span element that we just saw. Now, if we look at the JavaScript over here, we've got a query parameter that takes in whatever string we put in the search field. So the search field would be this one. So it saves it in the query parameter, and then if the query parameter is not empty, it calls the function doSearchQuery, and it takes in the string that we put in the search parameter. Now for doSearchQuery, what the function does over here is it takes in the element that has element ID search message, which we saw was this span element right over here. And then it uses .inner HTML to populate it with whatever value we put in the search parameter. So right away, what I'm seeing is user controllable input that changes the document object model. So what we're doing over here is whatever is in the search field is being used to change the content of the page. And so at first glance, this looks like it's vulnerable to DOM-based XSS. Now, when it comes to the DOM-based XSS payload, what we're going to try to do over here is break out of this span element. So if we right-click on this, and it doesn't look like it's allowing us to copy, but the idea over here is we've got span ID is equal to search message. And then this is our unique string right over here. And then we close the span element. So essentially whatever we enter in the search parameter right over here gets inputted in the page over here. So if we want to add a malicious cross-site scripting payload that alerts the user on a random string, what we could do is simply create an image element and say the source could be one, it could be really anything. And when it doesn't find the source right over here, it'll error out, and then we're going to say on error alert 1, and then we close the image tag. So over here, it'll see that there's a span of ID search message, and then it'll see that there's an image tag, and it'll execute it as part of the document object model. So our payload is this one. Let's copy it, put it in here, click on search. And here we go, we get alerted with the string 1, and we get the congratulations, you solved the lab message. So if we search on alert right over here to see how it interacted with the document object model, you could see over here, this is our span element, and then you've got our image element, and then this is the closing tag of our span element, just like we did right over here. All right, so we successfully completed the exercise by exploiting the DOM-based XSS vulnerability. In the next lab, we'll look at another case of a cross-site scripting vulnerability. Hi everyone, welcome back to another video in the Web Security Academy series. In today's video, we'll be covering lab number 5 in the cross-site scripting module titled DOM XSS in jQuery Anchor href attribute sync using location.search source. If you do not have an account on the Web Security Academy, you can get one by visiting the URL portswigger.net/websecurity and clicking on the sign up button. I already have an account and I am logged in, so to access the exercise, I'm going to click on Academy, select all labs, do a search on cross-site scripting labs, and then go to lab number 5. Titled DOM XSS in jQuery Anchor href attribute sync using location.search source. All right, let's get started. This lab contains a DOM-based cross-site scripting vulnerability. In the submit feedback page, it uses the jQuery library selector function to find an anchor element and changes its href attribute using data from location.search. To solve this lab, make the backlink alert document.cookie. All right, so the target goal over here is to exploit the DOM-based XSS vulnerability in the feedback page and make the button that says back or the link that says back alert on document.cookie, which outputs the cookies that are currently in session for that application. All right, let's access the lab. Now notice over here, this is the built-in browser in Burp, and so all my requests are already being passed in my Burp proxy. When it comes to DOM-based XSS vulnerabilities, I don't really use the proxy. Instead, I use the developer tools in the browser itself to understand exactly where my input is going. And so for this lab, we won't be using the proxy, we'll just be using the browser. Now, as usual, the first thing to do is map the application and see if any of the parameters could potentially be vulnerable to cross-site scripting. The way to do that is by putting in a string in the parameter that you think might be vulnerable and see if it's reflected back to the user or potentially even interacting with the document object model. So the first thing we're going to do is click on Submit Feedback. You're presented with a feedback form. Let's put in our input, and as usual, we want it to be unique. So let's say test.test.ca, and then test1, and let's say test2 for the message, and click on Submit Feedback. And what we're looking for is any input that is reflected back to the user. Now you could see over here, this is a generic message saying thank you for submitting your feedback. It's not actually reflecting any of the input that I put over here. And if we right click and click on inspect just to confirm and do a control find and check for the string test, which is what we put in the name, email, subject, and message field, you could see that there's 0 matches. So it's unlikely that the vulnerability is in one of these fields. So what I'm going to do is right click and view page source to see if there's any JavaScript that is writing to the document object model. So if you go down over here right away, I could see there is some JavaScript over here, and it's specifically to the ID backlink. So if we look for this ID, you could see it's for the back button. So if we go back right over here, this is the back string. So this is what I call the back button or the back link. And the JavaScript is being applied on this link right over here. And if we look at the JavaScript itself, it's saying for the attribute href of the element ID backlink, it's getting that attribute from window.location.search from the return path. Now, where is this return path set? So let's find it and view it right over here. And interesting. So return path right over here is equal to whatever is set in the URL. So this is really bad because the URL input is user controllable. And so anything that I put after the equal sign right over here gets added as the link for the backlink over here. Now in a real world scenario, what you could do is enter a malicious payload over here that maybe redirects the user to a malicious website or executes JavaScript in the user's browser that steals the user's session cookies, which is exactly what we're going to do. So since we can control this value right over here, we'll just add malicious JavaScript over here that outputs the user's cookie. And then when this application runs, it'll enter the input over here, so our exploit, and save it in the href attribute of the back button. And so whenever the user clicks the back button, our malicious payload is going to execute. So for the malicious payload, all we have to do in order to complete the lab is get it to alert on document.cookie, which essentially just outputs the cookies for this domain right over here. So to do that, we'll say JavaScript alert document.cookie. And that's essentially it. All we have to do is now put it in this parameter right over here. So the return path. And I could see it didn't copy JavaScript, so let's put it in here. And now when I hit enter, the application will run. That script that we just analyzed will run, and we'll save this payload in the backlink. And now every time you click on the backlink, it should execute my payload and it should alert on the cookies that are being used by this application. So let's hit enter. Right away, you see congratulations, you solved the lab message. But if we click on back over here, you could see this is the value that is stored in back. And so every time a user clicks on back, it'll output the content of the cookies for this application. Now we didn't log into the application and the application is not using any cookies, and so it's empty. But in a real world scenario, the application will be using cookies, and so it would alert on the cookies that the user is using. Of course, in a real world scenario, you would actually have an attacker controlled server where the cookies get sent to your attacker controlled server, and this way you have the victim user's cookies and you could compromise the user's account. So let's click OK, and that is it. So we successfully completed the exercise by exploiting the DOM-based XSS vulnerability. In the next lab, we'll look at another case of a cross-site scripting vulnerability. Hi everyone, welcome back to another video in the Web Security Academy series. In today's video, we'll be covering lab number 6 in the cross-site scripting module titled DOM XSS in jQuery Selector Sync using a hash change event. If you do not have an account on the Web Security Academy, you can get one by visiting the URL portswigger.net/websecurity and clicking on the sign up button. I already have an account and I am logged in, so to access the exercise, I'm going to click on Academy. Select all labs, do a search on cross-site scripting labs, and go to lab number 6, titled DOM XSS in jQuery Selector Sync using a hash change event. Alright, let's get started. This lab contains a DOM-based cross-site scripting vulnerability on the home page. It uses jQuery selector function to auto-scroll to a given post whose title is passed via the location.hash property. To solve the lab, deliver an exploit to the victim that calls the print function in their browser. Alright, so the target goal over here is to exploit the DOM-based XSS vulnerability to call the print function in the victim user's browser. Let's access the lab. Now notice over here, this is the built-in browser in Burp, and so all my requests are already being passed in my Burp proxy. When it comes to DOM-based XSS vulnerabilities, I don't really use the proxy. Instead, I use the developer tools in the browser. So for this lab, we won't be using the proxy and we'll just be using the browser. So usually what we do is we map the application and see if any of the parameters could potentially be vulnerable to XSS. The way to do that is by putting in a string in the parameter that you think might be vulnerable and see if it's reflected back to the user or potentially even interacting with the document object model. And so what we're going to do over here is first right click and then view page source and then look for any JavaScript that could potentially be taking client supplied input. And you can see over here we've got some JavaScript. If we scroll to the right, you could see that on the hash change event, so this is an event that is fired when the fragment identifier of the URL has changed. So when I say fragment identifier, that would be the part that is beginning and after the hash sign. So it would be hash, and then everything after the hash sign would be the fragment identifier. Now, the hash change event is triggered if this value over here changes. So when there is a change to that value, what it does is it essentially runs this entire thing right over here, which takes in the section tag. So if we go right over here, you could see it's this tag right over here, and it's looking for blog list. So this class right over here, and then it's looking for the h2 element. So if we go to the h2 element, this is what it's looking for. So either this h2 element, or this h2 element, or this h2 element, and so on. And then it's running this function right over here. So decode URI component window.location.hash.slice1. Essentially what this does is it splits the URL to everything that is after the hash sign, and then it outputs it, saves it in post, and then if post is not empty, it essentially scrolls to that value. So if we go back over here, the legitimate use of this functionality is to be able to scroll to a certain blog, and it's based on the headings, so the h2 element. So you can see over here, there's the cool parent, there is tracking your kids, there is what can 5G do for you, and then there is don't believe everything you read, and so on. So if we just copy, let's say the second one, so tracking your kids, go over here and put it after the hash sign, what should happen is this function should run. It should slice up my URL into just this one right over here and go to that specific link in the page. So let's hit enter. And here we go. You could see that it automatically scrolled down to this article over here. Now, if you want to confirm that that's what it's doing, all you could do is just like copy this. Go over here, right click, inspect, go to your console, put it in here, and then hit enter, and you could see what this piece of code is responsible for is really just slicing up the URL or segmenting the URL into whatever is after the hash sign. All right, so how could this be vulnerable? Well, whatever is after the hash sign is client controllable, and then it is being used in order to redirect the user to another page in the application. So the lab over here wants us to call the print function. So all we have to do is really insert our malicious JavaScript after the hash sign right over here. So the malicious JavaScript will be using an image tag. We'll say the source is equal to anything. In this case, we'll just say 1. And when it doesn't find this source for this image tag, it'll error out. And on error, I wanted to call the print function. So let's copy this, put it in here. So after the hash sign, now again, once I hit enter, it'll trigger the script right over here, and then it'll execute my malicious payload. So let's hit enter right over here. And here we go. You get presented with the print functionality. Let's click cancel. And if we go down right over here, you could see that we didn't get the congratulations, you solved the lab message. And the reason is because this function over here only triggers when there's a change to the hash function. So let's imagine this is a real world scenario when you copy this entire URL and send it to the user. What will happen is when the user clicks on that link, so let's actually do that right over here. So this is a new browser. The user enters, and the user is not presented with the print function. And the reason the user is not presented with the print function is because the script is only triggered when there's a change in the URL. And when you send the user this URL right over here, this was the original URL, and it would have to change for that script to run. So what we're going to do instead is we're going to put this application in an iframe where it only has the hash sign right over here and nothing after it. And then we're going to use the source attribute of the iframe to dynamically change the URL to include our payload right over here. And so when the user loads it up in their browser, what'll happen is it'll first load on this URL over here, and then it'll change the source attribute to include our print function. Since there's a change in the URL, it'll trigger this function over here, and we should be able to complete the exercise. So to do that, we're going to use the exploit server over here, which is just an attacker-controlled server. And the first thing we're going to do is see if we could even frame this application. Now, most applications won't allow for framing because it can be used in clickjacking attacks. So to frame an element, we'll just say the source is equal to the URL of the application, which is just this right over here. Let's copy this and put it in here and remove everything after the hash sign. So this is what will get loaded in the user's browser. Let's click on View Exploit. And perfect. So you could see over here, this is my iframe, and I've got the application in my iframe. Now this is what will load in the user's browser when the user clicks on the malicious website, which would be this one right over here. Now what I want to do is after it loads this URL over here, I want to change the URL to include my malicious payload. And since it is a change in the URL, it'll trigger the script that is vulnerable to DOM-based XSS. So in this case, I'll say onload. So after it's loaded, this .src is equal to the image tag. And src again, we said is equal to 1. It could be anything. On error is equal to print. And that's essentially it. This looks good. So essentially over here, again, the reason this would work is because first it'll load this URL over here, and then it'll change the URL to include this payload over here after the hash sign. And so since there is a change, the hash change event will be triggered, which will trigger the piece of code that is responsible for exploiting our DOM-based XSS. So let's deliver the exploit to the victim user. And here we go. We get the congratulations, you solved the lab message because the victim user clicked on the link. So they have an automated robot that clicks on the link. And if the victim user is presented with the print function, that means we completed the exercise. All right, so we successfully completed the exercise by exploiting the DOM-based XSS vulnerability. In the next lab, we'll look at another case of a cross-site scripting vulnerability. Hi everyone, welcome back to another video in the Web Security Academy series. In today's video, we'll be covering lab number 7 in the cross-site scripting module titled Reflected XSS into Attribute with Angle Brackets HTML Encoded. If you do not have an account on the Web Security Academy, you can get one by visiting the URL portswigger.net/websecurity and clicking on the sign up button. I already have an account and I am logged in, so to access the exercise, I'm going to click on Academy. Select all labs, do a search on cross-site scripting labs, and then go to lab number 7, titled Reflected XSS into Attribute with Angle Brackets HTML Encoded. Alright, let's get started. This lab contains a reflected cross-site scripting vulnerability in the search block functionality where angle brackets are HTML encoded. To solve this lab, perform a cross-site scripting attack that injects an attribute and calls the alert function. Alright, so the target goal over here is to exploit a reflected XSS vulnerability to call the alert function. Okay, let's access the lab. Now notice over here, this is the built-in browser in Burp, and so all my requests are already being passed in my Burp proxy. Alright, so as usual, the first thing we're going to do is look for input parameters that take client-side input that is reflected back to the user in the application. So a search field is a classic example of that. If we put test in here and click on search, you could see that our input is reflected back to us over here, and it could also be potentially reflected back in other places in the code that is just not visible to us through the browser. So if you click right over here and then search for the string test, you could see that we have two matches. So it's reflected back in the H1 element, so the heading. It's also reflected back in the value attribute of the input element. So that's interesting. We've got two places where it's reflected back to the user, and so these two places need to be tested for cross-site scripting vulnerabilities. The first thing I'm going to do is put in a character that is usually used for cross-site scripting attacks and see if the application encodes special characters on output. So if we click on search right over here and we look for the request, if we go down right over here, you could see that in the heading field, the angle bracket is URL encoded. So that's good. That means it might not be vulnerable to cross-site scripting and it might be vulnerable to cross-site scripting. So we don't really know. And in the value parameter, in the value attribute over here, it's also URL encoded. This means that we can't use the less than sign or the angle bracket in our exploit. This makes it hard to kind of exploit it in the heading parameter over here. However, we might be able to exploit it in the value attribute. So if we take this right over here and we copy this entire string and we put it in here, what we need to do is enter our payload over here. However, we need to enter it in such a way that it does not break the JavaScript. So the first thing that we're going to do is enter a double quote, which closes this double quote over here, which is provided for us already in the code. And then we're going to use an event called onMouseOver equal to alert 1, and then this double quote will be closed by the double quote that is provided for us. So let's copy this entire thing right over here. This would be the payload that we enter, and because we formatted it correctly, it shouldn't break the JavaScript in the input parameter right over here. So let's go back, put it in here, click on search, and here we go. It says, congratulations, you solved the lab. So the idea over here is when you do hover over it, you should get the alert message. And if we go back to the request over here, you should be able to see it in the response. So the alert over here, we're not exploiting it in this parameter over here, but we are exploiting it over here. So you could see that it was interpreted as JavaScript code and therefore it called the alert function. Alright, so we successfully completed the exercise by exploiting the reflected XSS vulnerability. In the next lab, we'll look at another case of a cross-site scripting vulnerability. Hi everyone, welcome back to another video in the Web Security Academy series. In today's video, we'll be covering lab number 8 in the XSS module titled Stored XSS into Anchor href attribute with double quotes HTML encoded. If you do not have an account on the Web Security Academy, you can get one by visiting the URL portsfigure.net/websecurity and clicking on the sign up button. I already have an account and I am logged in, so to access the exercise, I'm going to click on Academy, select all labs, do a search on cross-site scripting labs, and go to lab number 8 titled Stored XSS into Anchor href attribute with double quotes HTML encoded. Alright, let's get started. This lab contains a stored cross-site scripting vulnerability in the comment functionality. To solve this lab, submit a comment that calls the alert function when the comment author name is clicked. Alright, so the target goal over here is to exploit the stored XSS vulnerability to call the alert function. Let's access the lab. Now notice over here, this is the built-in browser in Burp, and so all my requests are already being passed in my Burp proxy. Alright, so when we're looking for cross-site scripting vulnerabilities, we're looking for client-side input that is stored and reflected back to the user, or just reflected back to the user. So if we click on View Post right over here, you could see under each post there are comments, and you could enter the comment that gets displayed under the post. And so this is your classic example of testing for XSS vulnerabilities, since anything that you put in the comment field and then the name field as well, and potentially the website and the email address, may be reflected back to you as the user. So the first thing that we're going to do is put in dummy values to see what is reflected to the user. So you've got test right over here, test1 over here, and then test.ca under the email field. And then under website, let's say http www.test.ca, and we'll post the comment. And then we'll go back to the blog to view our comment. So notice over here, definitely the name field is reflected back to us. The comment field is reflected back to us. And if we click on the name, then the href attribute, which is the website link, is also reflected back to us. So let's go to post ID 7 right over here and look at the response. So if we search for test, which was the string that we inputted over here, you could see that we've got 3 matches. Again, the first one is for the href attribute, the second one is for the name parameter, and then the comment parameter as well. Alright, so all 3 parameters need to be tested for cross-site scripting vulnerabilities. But before we do that, let's say less than and the double quote sign to see if anything is URL encoded by the backend application. Because if it is, that means that we need to get a little bit creative when it comes to exploiting cross-site scripting vulnerabilities. So the email field, let's keep it at test.test.ca since it doesn't get reflected back to us. And then the website, let's say less than and double quotes. Click on post comment. So far so good. It didn't reject my input. And if we go back over here and look at the response, we'll be able to view if it's URL encoded or not. So this is our previous comment. Now the comment after that, which we just did, you could see that the less than sign is URL encoded in the comment field and the name field. The same goes for the double quote. However, the less than sign is not URL encoded in the website field, but the double quote is encoded in the website field. So that's interesting. It looks like there's some kind of encoding rules over here that are not being applied on the href attribute, So we'll start off with testing that for cross-site scripting vulnerabilities. So let's copy this entire thing right over here. This is what it normally looks like with the link in between the double quotes. So what we're going to do is we're just going to add the exploit string JavaScript alert1, which just means that you're going to call the alert function when you click on the href attribute. So let's copy this, put it in here, and then just add test over here, and test.ca over here, and click on post comment. And here we go. It says, congratulations, you solved the lab. If we go back to the blog over here, all you have to do is click on this and then you get alerted with the string 1. So in a real world scenario, what you would do is you would have malicious JavaScript that either installs a keylogger in the user's browser or it steals the user's session cookies if the session cookies are not properly configured, and the user won't have any idea that it's happening when they click on your name field just to check your profile out. Alright, so we successfully completed the exercise by exploiting the stored XSS vulnerability. In the next lab, we'll look at another case of a cross-site scripting vulnerability. Hi everyone, welcome back to another video in the Web Security Academy series. In today's video, we'll be covering lab number 9 in the cross-site scripting module titled Reflected XSS into a JavaScript string with angle brackets HTML encoded. If you do not have an account on the Web Security Academy, you can get one by visiting the URL portswigger.net/websecurity and clicking on the sign up button. I already have an account and I am logged in, so to access the exercise, I'm going to click on Academy, select all labs, do a search on cross-site scripting labs, and then go to lab number 9 titled Reflected XSS into a JavaScript string with angle brackets HTML encoded. Alright, let's get started. This lab contains a reflected cross-site scripting vulnerability in the search query tracking functionality where angle brackets are encoded. The reflection occurs inside a JavaScript string. To solve this lab, perform a cross-site scripting attack that breaks out of the JavaScript string and calls the alert function. Alright, so the target goal over here is to exploit the reflected XSS vulnerability and call the alert function. Let's access the lab. Now notice over here, this is the built-in browser in burp, and so all my requests are already being passed in my burp proxy. As usual, when it comes to cross-site scripting vulnerabilities, what we're looking for is a parameter that takes in client-supplied input and then reflects it back in the response to the user without properly encoding the output. So over here, let's say test in the search functionality and click on search to see if the input is reflected back to us. And it is. So you could see over here, it's reflected in this heading over here. However, it might also be reflected in other parts of the code that are not directly visible to us in the browser. So if we go over here and search for the string test, you could see that there's 2 matches. The first one is the one that we do see in the browser, and then the second one is in a script tag. So it's in JavaScript. You could see the parameter is entered in a variable called search terms, and then search terms is being processed in this script right over here. Alright, so there's 2 locations that could potentially be vulnerable for cross-site scripting attacks. The first thing I'm going to do is just see if the application encodes the less than sign or the angle bracket, because that's usually how I test for cross-site scripting vulnerabilities. So if we go back to the response and we look for search results, you could see over here it is encoded, which means that we can't use this in our XSS attack. And if we go to the second location where we saw the parameter being reflected, it's also encoded over here. Now, since this is in JavaScript and in a script tag, we might be able to break out of this string right over here much easier than the heading parameter without using angle brackets. So the way to do that is we're first going to copy this. And let's remove the spaces. And this is where our regular string would be. So the first thing we need to do is close off this single quote over here. So let's close it off with another single quote. And then what you could do is use the semicolon sign to say that's the end of the line or the end of this command right over here. And then add your alert command, add another semicolon, and then you need to close this string over here so that you don't end up with any syntax errors. And that's essentially it. So let's copy this. This would be your exploit right over here. Let's put it in here, click on search. And here we go, we get alerted with the string that we put in the alert function, which is just 01. Let's click OK, and we get the congratulations, you solved the lab message. So if we go back and look at how it was interpreted, let's remove this over here, go down to the script tag. You could see over here that it was interpreted as code, and therefore our cross-site scripting vulnerability was executed. And it's important over here to note that we closed off this string over here with another single quote and then a semicolon and then the alert function and then another single quote over here, just so that we don't run into any syntax errors that could potentially not allow our alert function to execute. Now, there is another way of doing this, and that would be by just using the dash or the hyphen or the minus sign. Essentially, what happens is it'll cast this to an integer, so it'll end up having the value NaN. Because it's not a valid integer, this also ends up having the value NaN, and then when it reaches this, so it's this minus this, but this is a function, so it will execute it. And then if you minus it over here, it will also execute it. And then essentially, if you put an alert function just for search terms, you should end up with the value NaN, meaning that it wasn't really valid, but it does still execute our function. So let's copy this, put it in here. That's the second payload that you could use. Let's put it in here, hit search, and we should be presented with an alert function. And here we go. So we're presented with the window with the one string that we put in our alert function. Let's click OK. And that is it. So we successfully completed the exercise by exploiting the reflected XSS vulnerability. In the next lab, we'll look at another case of a cross-site scripting vulnerability. Hi everyone, welcome back to another video in the Web Security Academy series. In today's video, we'll be covering lab number 10 in the cross-site scripting module titled DOM XSS in document.write_sync using source location.search inside a select element. If you do not have an account on the Web Security Academy, you can get one by visiting the URL portswigger.net/websecurity and clicking on the sign up button. I already have an account and I am logged in, so to access the exercise, I'm going to click on Academy, select all labs, do a search on cross-site scripting labs, and go to lab number 10 titled DOM XSS in document.write_sync using source location.search inside a select element. All right, let's get started. This lab contains a DOM-based cross-site scripting vulnerability in the stock checker functionality. It uses the JavaScript document.write function, which writes data out to the page. The document.write function is called with data from location.search, which you can control using the website URL. The data is enclosed within a select element. To solve this lab, perform a cross-site scripting attack that breaks out of the select element and calls the alert function. Alright, so the target goal over here is to exploit the DOM-based XSS in the stock checker functionality and call the alert function. Let's access the lab. Now notice over here, this is the built-in browser in Burp, and so all my requests are already being passed in my Burp proxy. When it comes to DOM-based XSS vulnerabilities, I don't really use the proxy. Instead, I use the developer tools in the browser to understand exactly where my input is going. And so for today, we're not going to be using the proxy, and instead, we're just going to use the browser. All right, the first step is to map the application and see if any of the parameters that are user controllable could potentially be vulnerable to XSS. So we're going to click on View Details right over here. Go down, you could see we've got a check stock feature that takes in a few options in terms of which city the store is in. So let's just keep it at London and then click on check stock. And we see over here we've got 790 units for this specific item at this specific store. So at first glance, this doesn't seem like it might be vulnerable to cross-site scripting. However, depending on how this is coded and if it uses client-side code, we might be able to exploit it in order to perform a DOM-based XSS exploit. So let's inspect on this one first. And that didn't work properly, so let's right-click and inspect. Okay, interesting. So we've got a select element over here that has name, store ID, and then it takes the options, London, Paris, and Milan. And I could see over here, we've got JS scripts, one to check the stock check.js, and then we've also got stock check payload.js. So this is interesting. My guess is there is some kind of client-side JavaScript that is responsible for these options right over here. So let's right-click and just view the entire page source and go down right over here. And here we go. So we've got some custom JavaScript over here that is responsible for the stock check form. Let's review that JavaScript and see if it could potentially be vulnerable. So over here, we've got a variable called stores. It takes in an array that has 3 values, London, Paris, and Milan, which is what we saw right over here. And then if we go back, we've got another variable called store. And if we scroll to the right, you could see over here, it looks like store is taken from the URL parameter that is called store ID. So this is interesting because if we go back over here, we didn't see this in the URL. We only saw product ID is equal to 1. However, based on this, it looks like you could set the store ID in the URL and then it will be saved over here in the select element. And then the rest of the options will be displayed for you. So this is interesting. If we add store ID right over here to test out that functionality, let's say Paris 2, hit enter, go down, and here we go. So we get the option Paris 2 pre-populated for us, and then we've got the options London, Paris, and Milan. All right, so this is interesting. That means we've got a user controllable parameter, which is in the URL, and then it writes to the DOM. So it writes to the page of the application, which means that this is likely vulnerable to DOM-based XSS if the application does not properly validate an encode input. So what we're going to do over here is enter a variable in store ID and hopefully be able to break out of the select element. So if we go back over here, this is the select element that it's creating. And then we've got the option selected, Paris 2, and then option. So let's copy this if it allows us to copy it. And it does not. So essentially over here, whatever we put in the store ID parameter, so let's say Paris 2, gets saved in the following manner. So we've got option, and then over here, we'd have option selected. All right, so the idea over here is we need to break out of the first select statement and then the option statement. So if we go over here, the way it's structured is select, name is equal to store ID, and then we've got a bunch of options, and then we end the select statement. So when I enter my payload right over here in store ID, it'll be entered in this string over here. So what I'm going to do is keep this string right over here and then just say angle bracket / select. So what'll happen over here is that the application will pre-populate this with an option. So it'll end it with an option tag. And then over here, this string will end the select element right over here. And then I could add my payload right over here. So my payload would be, let's say, an image element. The source could be anything, let's say 1. And when it doesn't find that source, it'll error out. And on error, I want it to alert 1. And that's pretty much it. So let's copy this. This is our payload. Put it in here and then put it in our store ID. Hit enter. And we get presented with the alert box. Click OK, and we should see the congratulations, you solved the lab message. Let's hit enter again. Okay, and we see the congratulations, you solved the lab message. Now, if we go look at the source code over here to see how it was formatted, you could see over here we've got the select name, store ID, and then we've got our option pairs too, which I said it will close that option selected tag for us. And then we closed off this select over here. And then we added our image tag, which errors out, and then on error, it'll alert one, and then we've got the rest of the options. And that's pretty much it. So we successfully completed the exercise by exploiting the DOM-based XSS vulnerability. In the next lab, we'll look at another case of a cross-site scripting vulnerability. Hi everyone, welcome back to another video in the Web Security Academy series. In today's video, we'll be covering lab number 11 in the cross-site scripting module titled DOM XSS in AngularJS expression with angle brackets and double quotes HTML encoded. If you do not have an account on the Web Security Academy, you can get one by visiting the URL portswigger.net/websecurity and clicking on the sign up button. I already have an account and I am logged in, so to access the exercise, I'm going to click on Academy, select all labs, do a search on cross-site scripting labs, and go to lab number 11 titled DOM XSS in AngularJS expression with angle brackets and double quotes HTML encoded. Alright, let's get started. This lab contains a DOM-based cross-site scripting vulnerability in an AngularJS expression within the search functionality. AngularJS is a popular JavaScript library which scans the contents of HTML nodes containing the ng-app attribute, also known as an AngularJS directive. When a directive is added to the HTML code, you can execute JavaScript expressions within double curly braces. This technique is useful when angle brackets are being encoded. To solve this lab, perform a cross-site scripting attack that executes an AngularJS expression and calls the alert function. Alright, so the target goal over here is to exploit the DOM-based XSS vulnerability in the search functionality and call the alert function. Let's access the lab. Now notice over here, this is the built-in browser in Burp, and so all my requests are already being passed in my Burp proxy. When it comes to DOM-based XSS vulnerabilities, I don't really use a proxy. Instead, I use the developer tools in the browser. And so for today, we won't be using the proxy and we'll just be using the browser itself. As usual, the first thing to do is map the application and see if any user-supplied input is potentially changing the document object model. So the first thing we're going to do is put in a random string over here. Let's say 1, 2, 3, 4, 5. Click on search and then view the page source. So let's click on inspect and do a search on our string. So Control F, 1, 2, 3, 4, 5, 6. And actually we just put 1, 2, 3, 4, 5. And you could see over here there's only one match, which is what is reflected to me in the heading element. However, the first thing that I do notice over here is the ng-app keyword, which means that the application is using AngularJS. In fact, if we go to the heading element over here, you could see that the application is pulling down AngularJS version 1.7. So the application is definitely using AngularJS. Now, the important thing to note over here is that ng-app is a directive that tells AngularJS that this is the root element of the AngularJS application, and content inside the ng-app element can contain AngularJS code. And that's really what is going to allow us to perform our DOM-based XSS vulnerability. So all we have to do is use the syntax for AngularJS in order to perform our attack. And the syntax will be as follows. So we'll have 2 curly brackets, and then we'll use the $sign, and we'll explain what everything means in a bit. So we'll say on.constructor alert 1, and then we close our constructor, and that is pretty much it. So essentially over here, the $sign on is an event handler function in AngularJS, and the constructor is a function that when invoked executes its arguments, and its arguments over here is to call the alert function. So that's pretty much it. So let's copy this, put it in here, hit search, and we should be presented with an alert box, and we do. Let's click OK, and we get the congratulations, you solved the lab message. All right, so we successfully completed the exercise by exploiting the DOM-based XSS vulnerability. In the next lab, we'll look at another case of a cross-site scripting vulnerability. Hi everyone, welcome back to another video in the Web Security Academy series. In today's video, we'll be covering lab number 12 in the cross-site scripting module titled Reflected DOM XSS. If you do not have an account on the Web Security Academy, you can get one by visiting the URL portswigger.net/websecurity and clicking on the sign up button. I already have an account and I am logged in, so to access the exercise, I'm going to click on Academy, select all labs, do a search on cross-site scripting labs, and then go to lab number 12 titled Reflected DOM XSS. All right, let's get started. This lab demonstrates a reflected DOM vulnerability. Reflected DOM vulnerabilities occur when the server-side application processes data from a request and echoes the data in the response. A script on the page then processes the reflected data in an unsafe way, ultimately writing it to a dangerous sink. To solve this lab, create an injection that calls the alert function. So the target goal over here is to exploit the DOM-based vulnerability or the reflected DOM-based vulnerability to call the alert function. All right, let's access the lab. Now notice over here, this is the built-in browser in Burp, and so all my requests are already being passed in my Burp proxy. As usual with DOM-based vulnerabilities, we'll first start off with the browser and then we'll use the proxy if we need it. So the first thing we're going to do is put a random string in the search field and then inspect the page source, find all instances where this string was reflected. So you could see over here we only have one match and it's to the heading string that we see on the screen. However, if you look up here, you could see that there is a script that is being called and processed under the resources/js folder, and the script is called searchresults.js. So my guess is this script is involved in displaying the content on the screen when you put in a search field. So let's copy this and then view the script to see if there's any vulnerabilities in this script. All right, so it looks like over here we've got a function called search. It takes in a path. And if you look over here, based on the state of the request, it calls the eval function. So immediately when I see the eval function, the first thing that I want to look for is if it accepts client-supplied input, because the eval function is really dangerous. It allows you to run JavaScript. And so if it takes in client-supplied input, then we could potentially exploit this vulnerability. So over here, you could see it looks like it's creating a search results object, and then it's saving the response text in that object. So response text, as you can indicate, could potentially be coming from the client side. And then you could see over here, it calls a function called display search results, and it takes in the content of the variable that we had just set. So if we go back over here and we look at our request in Burp, you could see this is the request that is being performed when we put in a search parameter over here. And the response is some JSON text. So this is interesting. This is the response text over here that is being put in the eval function. And so if we could potentially change this response text over here, then we could exploit our vulnerability. So let's send this to repeater. Let's send again. When we put in a search field over here, you get the search term, and the content of your search field is inputted in this JSON string. So what we're going to do is try to break out of this string and then add another command that will be evaluated using the eval function. So the first thing to do is see if we could put in a double quote, because when we're entering something over here, it'll be entered, let's say, over here after the 5. And so this way we'll be able to close off this string over here, and then the next step would be to close off the entire JSON string. So let's hit send. Okay, so the double quote is escaped using a backslash. That's not a good sign for us as attackers because that means we might not be able to use the double quote. But before we make that assumption, let's see if it escapes the backslash character. So let's hit send over here. And it looks like it does not. So this is really good news for us as attackers because when you add a backslash over here, you're essentially escaping the escape that the application had introduced in order to escape the double quote. So essentially over here, this backslash is escaping this backslash and this double quote is not being escaped. So the next step over here is to close off the JSON string. So we'll add a curly bracket over here, hit send. Perfect, so far so good. You could see over here it's viewing this as part of the entire JSON string, but now we have these characters over here. So now we could introduce our other command that we want to be evaluated over here. So we'll add a semicolon and then the command is alert1 because the exercise wants us to display the alert box. Now we'll add a plus sign here for space because we want this to be URL encoded. We'll add a semicolon over here and then backslash backslash so that we could comment out the rest of the characters. So let's hit send over here and it looks like that did not work and I don't know why. So let's say alert 1 and then backslash backslash, hit send, and here we go. So you can see over here this entire thing is the JSON request and then we've got a new command and then the rest is commented out. All right, we're ready to exploit the vulnerability. So let's copy our exploit string, which was this entire thing over here. Let's put it in here and then copy it one more time and go back over here. Now, when I put this in the search field over here, what it should do is perform this request right over here, and then the eval function takes this response text over here and then executes it and displays the response in the request. So let's hit search and see if we're presented with an alert box. And we are not, so something is wrong with our exploit string. And I know what it is. So this backslash over here is introduced by the application itself. It shouldn't be introduced by us or else we'll have 3 backslashes. So the exploit string is this one right over here. It's not this one over here. So I just copied it from the wrong place. Let's copy this again, paste it, and hopefully now we should get our alert box, and we do. So click OK, and you should see the congratulations, you solved the lab message. Let's reload, click OK, and here we go. We see the message. Okay, so we successfully completed the exercise by exploiting the reflected DOM-based XSS vulnerability. In the next lab, we'll look at another case of a cross-site scripting vulnerability. Hi everyone, welcome back to another video in the Web Security Academy series. In today's video, we'll be covering lab number 13 in the cross-site scripting module titled Stored DOM XSS. If you do not have an account on the Web Security Academy, you can get one by visiting the URL portswigger.net/websecurity and clicking on the sign up button. I already have an account and I am logged in, so to access the exercise, I'm going to click on Academy. Select all labs, do a search on cross-site scripting labs and go to lab number 13 titled Stored DOM XSS. All right, let's get started. This lab demonstrates a stored DOM vulnerability in the block comment functionality. To solve this lab, exploit this vulnerability to call the alert function. Alright, so our target goal over here is to exploit the DOM-based XSS vulnerability in the block comment functionality and call the alert function. Let's access the lab. Now notice over here, this is the built-in browser in Burp, and so all my requests are already being passed in my Burp proxy. For DOM-based XSS vulnerabilities, I don't usually use the proxy. Instead, I just use the developer tools in the browser. And so for today, we're just going to be using the browser. Okay, the first thing to do is map the application and see if there are any client-supplied parameters that could potentially be vulnerable to cross-site scripting. So if we go down over here and click on View Post, we see that under each post, as a user, you could comment on the post. This is the classic example of where XSS vulnerabilities could potentially exist, specifically stored XSS vulnerabilities, because the comment does get stored in the application, and so we're not just dealing with a reflected XSS, we're dealing with a stored XSS. So as usual, the first thing we're going to do is just put in random input, let's say test1, and then email is test@test.ca, and the website is http://www.test.ca, and post a comment. Go back to the blog, and if we go down over here, you could see that our comment has been posted under the blog, and we've got the comment field is posted under the blog and also the name field. Now, if we hover over the name field, we don't actually get linked to the website of the user. And so we've got two locations that we want to test for cross-site scripting, and that's the comment field and the name field, because those are the only ones that are displayed back to the user. So if we right-click right over here and then click on Inspect, and we do it again, you could see over here, this is where my comment got added. So test over here is my comment, and then if we open that p tag over here, you should see the author, and the author over here is test1, and it looks like there is an href element, it's just not directly visible from the application itself. So the first thing that I'm noticing over here is there's a script tag that calls a custom script called load comments with vulnerable escape html.js. So I definitely need to review this script just based on its name. So let's copy the link address and post it in here. And here we go. This is the script that gets run, I'm assuming, in order to populate these fields right over here. So if we go down in the script, you could see display comments. So definitely the script that is responsible for displaying comments. It takes in the comments of the user, and then it actually creates your document object model for the page. So it generates the p element, and then depending on the script, it generates the image element and so on. You could see over here, it actually calls a function called escape HTML in order to, I'm assuming, escape dangerous characters that could lead to an XSS vulnerability. And we'll look at that in a bit. But if you see over here, it does that for author as well. So it calls the function on the author user. It also does it for the comment section over here. So it calls it on the comment body, which we saw was this right over here. So if we do a search on escape HTML, so let's copy it and then find. Here we go. This is the function. All it does is use the .replace JavaScript function in order to replace angle brackets. So it replaces the less than sign, and it also replaces the bigger than sign with the URL encoded versions of those signs. So I'm seeing where the vulnerability is over here. .replace only replaces the first instance of the character that is right over here and the character that is right over here. It doesn't actually replace all the instances in the string. And to prove that, what we could do is add a comment that contains the angle brackets. So let's say less than, bigger than, and then let's say less than, and then add the string test, and then bigger than right over here. And then let's add a random name, and email is just test@test.ca, and the website is http://test.ca, and post a comment. Go back to the blog right over here, and we'll go to the last comment over here. So if we look over here, and we're looking for the content in the comment. So you could see over here, it only displays a portion of the comment. So that's interesting. If we look here, you could see the way it interpreted it is it looks like it URL encoded my first less than and bigger than signs, and then the rest, which was in a test tag, it actually viewed it as code. And so this is definitely vulnerable to cross-site scripting. And to prove it even more, what we could do is go to the console right over here and then copy this entire function. Put it in the console. So we're just defining a function called escape HTML, and then we're calling escape HTML on the comment body. So let's copy this, enter, and here we go. So you could see that this further proves that the escape HTML function only URL encodes the first instances of the angle brackets and doesn't URL encode all the instances of the angle brackets. And so it's definitely vulnerable to cross-site scripting, and the way to exploit it is just simply add the first instance of the angle brackets, which will be URL encoded, and then just add an image tag that has a source that doesn't exist, let's say 1, and then when it errors out because it doesn't find the source, call the alert function. And that's pretty much it. So let's copy this, let's close this off, add this in the comment, and then let's say test.test.ca, and then the website is http test.ca, post a comment, go back to the blog, and here we go. We get alerted with the string 1. Click OK, and it says, congratulations, you solved the lab. All right, so we successfully completed the exercise by exploiting the stored DOM-based XSS vulnerability. In the next lab, we'll look at another case of a cross-site scripting vulnerability. Hi everyone, welcome back to another video in the Web Security Academy series. In today's video, we'll be covering lab number 14 in the cross-site scripting module, titled Exploiting Cross-Site Scripting to Steal Cookies. If you do not have an account on the Web Security Academy, you can get one by visiting the URL portswigger.net/websecurity and clicking on the sign up button. I already have an account and I am logged in, so to access the exercise, I'm going to click on Academy, select all labs, do a search on cross-site scripting labs, and select lab number 14, titled Exploiting Cross-Site Scripting to Steal Cookies. All right, let's get started. This lab contains a stored XSS vulnerability in the block comments function. A simulated victim user views all comments after they are posted. To solve the lab, exploit the vulnerability to exfiltrate the victim's session cookie, then use this cookie to impersonate the victim. And then we have a note over here saying to prevent the Academy platform from being used to attack third parties, our firewall blocks interactions between the labs and arbitrary external systems. To solve the lab, you must use Burp Collaborator's default public server. So since we do need to use Burp Collaborator, that means we'll be using the professional version of Burp. All right, so the target goal over here is to exploit the stored XSS vulnerability in the block comment functionality to steal the victim's session cookie and then log in as the victim. Let's access the lab. Now notice over here, this is the built-in browser in Burp, and so all my requests are already being passed to my Burp proxy. All right, as usual, the first step is to find a cross-site scripting vulnerability. And the way we do that is we see if there's any functionality in the application where it reflects user-supplied input. So if we go down right over here, you could see that we could view posts. We click on that button, and then go down and see that there's a comment functionality, and whatever comment we post gets posted under the application itself. So if this doesn't properly validate input and encode it on output, then it could potentially be vulnerable to a stored cross-site scripting vulnerability. So let's first add a normal comment and see which fields are being reflected. So let's say test1 for the name, and then the email is test@test.ca, and the website is http www.test.ca, and we post the comment, and then we go back to the blog and go down. You could see over here, we've got the name field is being reflected back to us. Also, if you click on the name field, the website field is also reflected back to us, and then the comment field is reflected back to us as well. So all three fields need to be tested for stored cross-site scripting vulnerabilities. We'll start off with the comment field, and if it's not vulnerable, then we'll move on to the name field and then the website field. So we'll test for cross-site scripting using a really simple payload that just outputs a certain string to the web console. So we'll say script console.log, and we'll output the string hello, and then we'll end the script, And then for name, we'll just say test again, and email test@test.ca. And then website is http://www.test.ca and post a comment. Now let's go back to the blog, go down. Now notice over here, our comment does not get displayed. This is the first indication that it was viewed as client-side code and executed as client-side code. But just to confirm, we're going to right-click, click on Inspect, and then we're going to go to the console over here. And here we go. You see that it did print out that string in the console. And so definitely this is vulnerable to cross-site scripting. Now the next step is to see if this cross-site scripting vulnerability has an impact. And so what we're going to do is steal the session token cookie of anyone that visits this page over here. And to do that, we need to build our script. We'll do that in the notes.txt document, which I'll leave a link to in the description. So we'll start off with the script tag. And then we'll use fetch in order to output the cookie of the user that visits the page and then send it to our attacker controlled server. So over here, we'll have the URL to our attacker controlled server, which I'll add later. And then over here, we'll add the configuration for the request itself. So we'll say the method is a post method. The body is document.cookie. Essentially what this does is it says when you perform this request to our attacker controlled server, then in the body of the request, add the cookie of the user that visited the page. And then we'll say mode is no course. All right, so we add the mode to be no course over here because we don't want it to output a client-side error. So if you don't add this right over here, what will happen is that the browser will try to fetch the response of the request that you're performing to your attacker-controlled server. And since the browser is coming from a different domain than the attacker-controlled server, there will be a course error outputted that says, hey, you're not allowed to view the response. Now, this is a client-side error that will only appear in the web console. So view inspect, and right over here under the console, it'll appear. It won't actually prevent the exploit from working. However, we want this to be as discreet as possible, and so we don't want it to output any errors, and therefore we say no course, meaning that we don't actually want to view the response of the request. We just want it to perform the request. All right, this looks good. Let's add our semicolon over here. Let's copy this, close this off, put it in the comment field. And actually, we forgot to add the link to our attacker-controlled server. So if we go over here and then go to Collaborator and then say Get Started and copy it to Clipboard right over here and paste it in here. So this is the link to our attacker-controlled server. This is the reason we needed to use Burp Suite Professional because it provides a server for us without us having to configure one. So we'll add HTTPS right over here. And so essentially over here, what's going to happen is when we post the comment, there's a simulated robot in the backend that is viewing the comments on all the posts. And essentially when it views the comment on this post right over here, the script will run and then it'll perform a post request to our attacker controlled server. And in the body of the request, it's going to retrieve the cookie of the user that is viewing the page. And since this user is logged in, it'll retrieve an authenticated cookie, and then we're going to use that cookie to log in as the user. So let's copy this. Paste it in here. And then name is test, email is test@test.ca, and then website is just the regular website, test.ca, and post the comment. Now we wait for the simulated user to view the blog, and we go back over here and click on Poll Now. And here we go. We get a ping to our attacker-controlled server, and if we click right over here, you could see it's coming from the source IP 34.251.122.40. So that's the public IP of our victim user. And then if we look at the request to collaborator, the body of the request should include the session token. And it does. So over here, there were two cookies that were set for the user. One is secret and the other is session. I'm not sure what secret is, but I know session is definitely a session cookie. So what I'm going to do is copy this session cookie and then set it in my browser to see what type of user we just compromised. So if you right click over here and then inspect, go to application, and then under session over here, this is our unauthenticated session cookie. We're just going to add the authenticated one that we just compromised and then go to home. And right away you see we've got congratulations, you solved the lab. But if we go to my account over here, you could see that we've compromised the administrator session cookie, which means that it was the administrator that viewed our post. All right, so we successfully completed the exercise by exploiting the stored cross-site scripting vulnerability in order to steal the administrator's session cookie. In the next lab, we'll look at another case of a cross-site scripting vulnerability. Hi everyone, welcome back to another video in the Web Security Academy series. In today's video, we'll be covering lab number 15 in the cross-site scripting module titled Exploiting Cross-Site Scripting to Capture Passwords. If you do not have an account on the Web Security Academy, you can get one by visiting the URL portswigger.net/websecurity and clicking on the sign up button. I already have an account and I am logged in, so to access the exercise, I'm going to click on Academy. Select all labs, do a search on cross-site scripting labs, and select lab number 15, titled Exploiting Cross-Site Scripting to Capture Passwords. All right, let's get started. This lab contains a stored XSS vulnerability in the block comments function. A simulated victim user views all comments after they are posted. To solve the lab, exploit the vulnerability to exfiltrate the victim's username and password, then use these credentials to log into the victim's account. And we've got a note over here saying to prevent the Academy platform from being used to attack third parties, our firewall blocks interactions between the labs and arbitrary external systems. To solve the lab, you must use Burp Collaborator's default public server. So because we are using Burp Collaborator, we will be using the professional version of Burp for today's lab. All right, so the target goal over here is to exploit the stored XSS vulnerability in the block comment functionality to exfiltrate the victim's username and password, and then use the exfiltrated username and password to log in as the victim user. Let's access the lab. Now notice over here, this is the built-in browser in Burp, and so all my requests are already being passed in my Burp proxy. All right, so as usual, the first step to finding cross-site scripting vulnerabilities is to find a client-supplied parameter or a client-controlled parameter that is reflected back in the application. So if we go down right over here, you could see we've got posts. You click on View Post, and you go down, there's a comment functionality, and any comment you post over here gets posted in the application. And so this definitely should be tested for stored cross-site scripting vulnerabilities. The first thing that we're going to do is just put in random data. Let's say test, name test1, and then email test@test, and the website http www.test.ca, and then post a comment over here, and then go back to the blog post to see what's reflected in the application. You could see the comment field is reflected, the name field is reflected, and if you click on the name field, the website is also reflected. So all three parameters need to be tested for stored cross-site scripting vulnerabilities. And we'll start off with the comment field, and if it's not vulnerable, we'll move on to the name field. So the first thing we're going to do is supply a really simple payload for cross-site scripting and see if it's being interpreted as client-side code. So let's say script console.log, and we'll just say hello, and then end our script. All this does is essentially print the word hello in the web console. Of course, if this is not vulnerable to cross-site scripting attack, then this should just be interpreted as a string, and we should see it right over here under the comments, and it shouldn't interact with the client-side code. In the name field, we'll just say test, and then test@test.ca, and the website, just www.test.ca, and post a comment. All right, let's view the blog post over here and go down. Right away, I could see that my XSS payload is not visible to me in the application, which means that it was interpreted as client-side code. But if we right-click over here and click on Inspect, we could confirm it by going to Console over here. And here we go. You could see my message hello has been printed on the console, which means that this is definitely vulnerable to cross-site scripting attacks. Now, we do have to show impact for the cross-site scripting vulnerability. And so for this lab, what we're going to do is we're going to add a username and password field. And what's going to happen is the simulated victim user, essentially a robot in the backend, will see that you've got a username and a password field and will think that they need to log in again, and they will supply their username and password. And when they do that, the username and password will be sent to my attacker-controlled server, and then I'm able to compromise the user's account. All right, so to do that, we need to write a really simple script. So we'll say input name is equal to username. So that would be the username field. And we'll say the ID is username. And then we'll add another input parameter that is of type password. And then name is equal to password. So this essentially is the username parameter that will be displayed over here, and then another one will be displayed for the password parameter. Now for the password parameter over here, I'm going to use the onChange event, which is an event that occurs when the value of the HTML element is changed. So essentially when the user enters their password, then it'll run this code right over here. So let's close that over here. And the code will be if this .value.length, then fetch our attacker-controlled server, which I'll add later. And then the configuration for the request will be as follows. The method is a post method. The mode is no course. And again, I'll explain this later as well. And then the body is username.value plus semicolon this dot value, which is just the value of the password field. And that's essentially it. We're missing a bracket over here and then a semicolon. All right, so essentially what this does is it presents a user with a username field and a password field. Now, when the user puts in their password, it'll trigger the onChange event, and then this code will run over here. So in this code over here, we've got an if statement that says this .value.length. So if the length of the password field changes or is bigger than 0, which means that the user put in their password, then perform a request to my attacker-controlled server. And I want it to be a post request where the body of the request is the value that was put in the username field. And then we've got a semicolon to separate the username from the password. And this .value is just the value of the password field. Now, we do use the mode no course, which means that I don't want to view the response of the request. So course stands for cross-origin resource sharing. What it does is essentially, because of the same origin policy, what happens is when you perform a request to another origin, you're allowed to perform the request, you're just not allowed to view the response. So if we don't include this right over here, it'll try to retrieve the response of our post request to the attacker-controlled server. And because it's from a different origin, it'll output a client-side error in the web console. And we don't want it to output an error just because we want to be stealthy. The attack will work either way, but we don't want it to be output an error. And so we add the mode no course, which essentially means that I don't want to view the response of the request, just perform the request itself. And that's pretty much it. So let's go to Burp, go to Collaborator over here, copy to Clipboard, and add our attacker-controlled server link over here, HTTPS. And here we go. Let's copy this, paste it in here. Hopefully we don't have any errors in our script. Let's say the name is test, and the email is test@test.ca. And the website is www.test.ca. Post a comment. Now, if we go back to the blog over here and go down, you could see there is a username field and the password field. Now, this attack is not very sophisticated. In a real-world scenario, you'll present the user with a window that says, hey, you need to log in again. Please put your username here and your password over here. And so it'll seem much more realistic to the attacker. But this is enough to complete the lab. And so if we go over here and click on Poll Now, you could see that someone did fill in the username and password, and that would be our victim user over here that is coming from the source IP 34.253.173.2. And if we make this a little bit bigger, you could see the request to the collaborator. Now, the body of that request should include the username and password of the user that filled in these fields right over here. And we're lucky. We had an administrator user fill it in. So let's copy the password over here. Go up, click on my account, put in the username administrator and then the password that we just compromised and hit login. And here we go. We were able to log in as the administrator user. All right, so we successfully completed the exercise by exploiting the stored XSS vulnerability in order to harvest user credentials. In the next lab, we'll look at another case of a cross-site scripting vulnerability. Hi everyone, welcome back to another video in the Web Security Academy series. In today's video, we'll be covering lab number 16 in the cross-site scripting module titled Exploiting XSS to Perform CSRF. If you do not have an account on the Web Security Academy, you can get one by visiting the URL portsugar.net/websecurity and clicking on the sign up button. I already have an account and I am logged in, so to access the exercise, I'm going to click on Academy. Select all labs, do a search on cross-site scripting labs, and go down to lab number 16 titled Exploiting XSS to Perform CSRF. All right, let's get started. This lab contains a stored XSS vulnerability in the block comments function. To solve the lab, exploit the vulnerability to perform a CSRF attack and change the email address of someone who views the block post comments. You can log into your own account using the following credentials, and we're giving credentials for a regular user. All right, so the target goal over here is to exploit the stored XSS vulnerability in the block comment functionality to perform a CSRF attack that makes the victim user change their email address without knowing that they did that. All right, let's access the lab. Now notice over here, this is the built-in browser in Burp, and so all my requests are already being passed in my Burp proxy. I am using the professional version of Burp, but you don't actually need to have the professional version. All the features that I use over here are available in the community version. All right, so the first thing I'm going to do over here is log into the account that we were given and look at how the change email functionality works. So let's log in with the username, and the password was Peter, hit login. Now over here, you have the ability to update an email. So let's say test.test.ca and click on update email, and we'll review that request in Burp. So let's send this to Repeater. This is the request that is responsible for changing an email address. It's to the /myaccount/change email endpoint. And if you go down right over here, it takes in two parameters, the email field and the CSRF field. Now the email value we know because we want to change it to the attacker-controlled email address. However, the CSRF parameter we don't know. So for those of you that are not familiar with CSRF, it stands for cross-site request forgery. It's a type of attack where the attacker gets the victim user to unintentionally perform a request on behalf of the attacker in the session of the victim user. So the idea over here is you send a phishing link to the user, and in that phishing link, there's an automatic request that gets performed in order to change the user's email address, and this all happens without the user knowing. Now, to prevent this type of attack, the application uses CSRF tokens, which are random tokens that are stored in the user's client-side code. Now, since the attacker has no way of knowing that CSRF token, when the attacker tries to perform that automatic request, the request will be rejected because you don't have a proper CSRF token. However, if there is a cross-site scripting vulnerability in the application, then what we could do is perform a request to first obtain the CSRF token from the application, which is the /myaccount endpoint, and then perform another request in order to get the user to change their email address. And that's essentially what we're going to do. But first, we need to find a cross-site scripting vulnerability. So let's go to Home and click on View Post and go down. Now notice over here, you have the ability to add comments on each post. And since the comment and potentially the name are reflected back to the user, then it definitely needs to be tested for cross-site scripting vulnerabilities. So we'll start off with just testing the comment field using a really simple script. So we'll say script console.log, and we'll just print out hello. And we'll end the script. And in the name field, we'll just say test, and then the email test@test.ca, and the website will just say www.test.ca. So essentially all this does is it'll print out the message hello to the web console. Of course, this is only going to happen if the application views this as client-side code, which means that it would be vulnerable to cross-site scripting. However, if it's not vulnerable to cross-site scripting, what the application will do is view this as a string, and then it should be just displayed in the comment and does not interact with the code at all. So let's click on post comment right over here. Go back to the blog, go down. And this is interesting. So you could see that my comment is not showing, which means that it was definitely viewed as client-side code and executed as client-side code, which means that this is vulnerable to cross-site scripting. But just to confirm, we're going to right-click and click on Inspect over here, and then go to Console. And here we go. Here's the message hello that we use the script to print. And so because we do see the message, definitely our script was executed and the comment field is vulnerable to cross-site scripting. All right, so now we have a cross-site scripting vulnerability. We're going to use that cross-site scripting vulnerability to first perform a GET request to this endpoint over here, and then retrieve the CSRF token from the response of this request. And once that's done, we're going to perform the POST request to change the email address of the user. All right, so to do that, we're going to write a really simple script. So we'll start off with this script tag. I'll add the link to this document in the description of the video. We'll first initialize our request, so new XML HTTP request. This will essentially allow us to perform the request and then also to view the response of the request. So we're going to say rec.onload, call the function handle response, which we'll write in a bit. And then we'll say rec.open, perform a GET request to the endpoint /myaccount, and we'll set this to true. So essentially over here, what we're doing is we're making a request to the /myaccount endpoint. And the reason we're doing that, we go to proxy right over here and look for that endpoint. The reason we're doing that is because this endpoint contains our CSRF token. So let's match on CSRF, and here we go. So we're looking for the CSRF token, which is in the value field of the input element that has name CSRF. Now, usually when you're performing a request and then trying to view the response of the request, the same origin policy of the browser will prevent you from viewing the response of the request unless the request is coming from the same origin. So the same URL where this response is. However, because cross-site scripting vulnerabilities run within the application itself, we are coming from the same origin. And so it'll allow us to view this response over here, and then we could extract the CSRF token of the victim user from it. And that's what we're going to do. So we'll say rec.send. And then we'll define our function, handle response, which essentially performs these two requests. So the first one is to retrieve the CSRF token, and the way we're going to do that is by saying this.response text.match. We're looking for the element that has name CSRF, and then we want to match on the value of the element. So for this, we're going to use regex, and bear with me for a little bit, W+, and then we've got one right over here. So essentially what this does is it looks for the input element that has name CSRF, and then it matches the regex on the input element. And when we're saying W+, we're just saying all the word characters in the value attribute, which is the alphanumeric characters. And then we're matching on the first one. All right, so we've retrieved our token, and then we're just going to create a new variable called change_rec. So that's a new request. And we'll say change rec.open. So the next step over here, after we've performed this get request, is to perform the post request that was responsible for changing the email address right over here. So it's to the endpoint /myaccount/email address, and it takes in two variables, the CSRF token, which we just extracted, and the email address of our victim user. So it's a post request, and it's to the my account. So /myaccount /change email endpoint. And then we need to send the parameters in the request in the body of the request. So we'll say send CSRF is equal to the token that we just extracted plus the email address of our attacker controlled server. So let's say test3@test.ca. So this has to be a unique email address, so we can't use the email address that we used previously. All right, and this looks good. Let's end this, and then we end our script function. Hopefully we don't have any errors. Let's copy this and then put it in the comment field. And let's make this a little bit smaller. And then let's say test. Email is test@test.ca. And the website is http://www.test.ca. So essentially over here, when we click on post comment, it'll post the comment and store the script under this post over here. When the victim user visits this post, the script will run, and what it'll do is it'll first extract the CSRF token from the /myaccount page of the user, and then it'll use that CSRF token to perform the post request to change the email address of the user to test3@test.ca, which is an email that the attacker controls. And then the next step over here would be to use the email address in order to reset the user's password. But to complete the exercise, all we have to do is change the user's email. So let's click on post comment. And here we go. We immediately get congratulations, you solved the lab, which means that the victim user's email address got changed. All right, so we successfully completed the exercise by exploiting the stored XSS vulnerability in order to perform a CSRF attack and change the email address of the victim user. In the next lab, we'll look at another case of a cross-site scripting vulnerability. Hi everyone, welcome back to another video in the Web Security Academy series. In today's video, we'll be covering lab number 17 in the cross-site scripting module titled Reflected XSS into HTML Context with most tags and attributes blocked. If you do not have an account on the Web Security Academy, you can get one by visiting the URL portswigger.net/websecurity and clicking on the sign up button. I already have an account and I am logged in, so to access the exercise, I'm going to click on Academy. Select all labs, do a search on cross-site scripting labs, and go to lab number 17, titled Reflected XSS into HTML Context with most tags and attributes blocked. All right, let's get started. This lab contains a reflected XSS vulnerability in the search functionality, but uses a web application firewall to protect against common XSS vectors. To solve the lab, perform a cross-site scripting attack that bypasses the WAF and calls the print function. And we've got a note right over here saying your solution must not require any user interaction. Manually causing print to be called in your own browser will not solve the lab. So the victim user that will be sending this malicious link to will not perform any action in the browser, and therefore we need it to trigger when the user just visits the link. All right, so the target goal over here is to perform an XSS attack that bypasses the WAF and calls the print function. Let's access the lab. Now notice over here, this is the built-in browser in Burp, and so all my requests are already being passed in my Burp proxy. I am using the professional version of Burp. However, all the features that I'll be using are also in the community edition. It just Intruder is much faster in the professional version. And so I've decided to use the professional version for this lab. All right, so the first thing that we do when it comes to testing for cross-site scripting vulnerabilities is we look for client-supplied parameters that are reflected back in the application. So we've got a search functionality over here. The first thing I'm going to do is just put in a string and click on search and see if my string, which is a client-supplied input, is reflected back in the application. And as you can see over here, it is reflected back to me. And so this field needs to definitely be tested for cross-site scripting vulnerabilities. The first thing I'm going to do is test a really common exploit. So we'll use the script tag to call the alert function and see if the application allows us to use that tag. So let's click on search and we get tag is not allowed. So just like the description said, there is a web application firewall or a WAF that is filtering some of the tags. And in this case, the script tag is not allowed. So the next step over here is to figure out which tags are allowed so that we could bypass the firewall. So let's just keep script right over here. Click on search again and send this request to Intruder. And in Intruder over here, we're going to clear on everything except this right over here. So this doesn't really need to be URL encoded. So I'm just going to remove the URL encoding over here and add this. So essentially what we're going to do is we're going to try all the different possible tags over here. And whenever we get a tag is not allowed or an error code, that means that that tag is not allowed. However, if we do get a 200 OK message, that means the tag is allowed. So for that, we're going to go to payloads over here and we're going to add our payload list in here. Now to get the list of tags, we're going to Google XSS, cheat sheet, port swigger, hit enter, and it should be the first entry over here. So let's click it. And this is a really, really useful resource for cross-site scripting. It essentially has all the tags and then the custom events that you could use on each tag and so on. And it does it for each browser. So for now, we're just going to copy all the tags, paste them in here, and then try all 152 tags to see which ones work. And this is why I'm using the professional version. You could still use the community edition. It's just that the professional version is much faster and I don't want you to sit and wait in the video while I wait for the automated attack to complete. So let's click on start attack. And so far you could see there's a ton of 400s, which means that they're not allowed. But you could see over here there's a 200. So let's order on status to see what's allowed. So we've got body tag is allowed and then custom tags are allowed. Let's try with body tag, and if it doesn't work, we'll go for the custom tag. So let's close this off over here, discard, and just test it over here. Let's go back and just put in the body tag to confirm that it is allowed. Hit search, and here we go. So we don't get that custom error from the WAF. We get a 200 OK message, and you could see over here it's not reflected back to me in the input, which means that it's being viewed as client-side code. So the next step over here is to copy the events to clipboard and see which events are allowed. And then let's clear this, paste it in here. So these are the events that we want to test to see which ones are allowed. And then in positions over here, we no longer need this. We'll just put the body tag. And then let's just say event, I'm making this up as I go, is equal to, let's say 1. So over here, this is the field that we want to test for valid events over here to see which events work. Now first, let's URL encode this. So Control U to URL encode it. And then over here, let's add this to the list to make sure that's the field that we automate. All right, so what it'll do is in this field, it'll try each and every payload. So let's click on Start Attack. And again, you see a bunch of 400s, but you also see a bunch of 200s. So let's order on the 200 OK messages, and we're allowed to use on before input, on resize, on scroll end, on after print, and so on. I'm going to go with on resize. So over here, we already have the body element selected, and then I'm just going to look for on resize. And here we go. And then it just gives you the code for the XSS vulnerability over here, which is why I said this tool is really, really useful. And even better, because we're testing with Chrome and the victim user is likely going to be using Chrome, you could select which browser and then it'll only show you the code that will work on that browser. In this case, this is compatible with all of them. So I'll just copy this over here and put it in here and then go back to our application and then add it over here and click on search. Now notice over here, when we resize the browser, it should present us with the print functionality, and it does. So let's cancel over here, and it'll do that on a loop, which is not great, but let's close this over here. Now we know that our script is working, and let's access the lab again. Now, the issue with this is that when you try to do this with a victim user, what you're going to do is essentially send them this link right over here. So if we go back to proxy, and look at the request that was calling the print functionality, it's this one right over here. If you copy this, add HTTPS to it, and then go back to proxy, and we don't need this anymore. Let's close this off. And then copy the payload. If you send this link to the user won't be presented with the print function. And to demonstrate that, let's copy it and just go to a new browser. So let's say Firefox, and then try it right over here. You could see the user is not presented with the print function. And the reason is because this is only triggered when you actually resize the window. And unless the user resizes the window, the user will never be prompted with the print functionality. And the lab did say that the user won't be performing any actions. And so that's why we need to add a little bit of extra code in order to resize the browser itself, or maybe an iframe, and then it'll automatically work when we send the exploit to the user. And for that, we're going to use the exploit server, which is just our attacker-controlled server. In here, we're going to see if the application can be framed. So most applications can't be framed because it opens an attack vector for clickjacking attacks. But let's see if the application can be framed in this case. So let's say src is equal to the URL to the application. So let's copy this, paste it in here, and then just close it off and close off our iframe. Let's view the exploit. And you could see over here, what we're doing is we have an iframe, and then we're just loading the page in the iframe. So what we're going to do right now is essentially perform the resizing option in the iframe itself, and therefore it'll be an automated process where the user won't have to do it themselves. So to do that, the first thing we're going to do is just copy this entire thing over here and put it in here. So this will trigger the print functionality, and then we're going to say onload this dot style dot width is equal to 100 px. And I'll copy this and put it in here, and I'll add the link to the document, so the notes.txt document, in the description of the video. All right, let's deliver our exploit to the victim user. If the user is presented with the print functionality, you should see congratulations, you solved the lab message. All right, so we successfully completed the exercise by exploiting the reflected XSS vulnerability to call the print function. In the next lab, we'll look at another case of a cross-site scripting vulnerability. Hi everyone, welcome back to another video in the Web Security Academy series. In today's video, we'll be covering lab number 18 in the cross-site scripting module titled Reflected XSS into HTML Context with all tags blocked except custom ones. If you do not have an account on the Web Security Academy, you can get one by visiting the URL portsfigure.net/websecurity and clicking on the sign up button. I already have an account and I am logged in, so to access the exercise, I'm going to click on Academy. Select all labs, do a search on cross-site scripting labs, and then go to lab number 18. titled Reflected XSS into HTML Context with all tags blocked except custom ones. All right, let's get started. This lab blocks all HTML tags except custom ones. To solve the lab, perform a cross-site scripting attack that injects a custom tag and automatically alerts on the document.cookie. All right, so the target goal over here is to perform an XSS attack that alerts on document.cookie. So it displays the cookie of the user. All right, let's access the lab. Now notice over here, this is the built-in browser in Burp, and so all my requests are already being intercepted in my Burp proxy. I am using the professional version of Burp, however, all the features I'll be using are also in the community edition, and so you don't really need the professional version. It's just that for the intruder portion of the attack, I don't want to sit and wait when using the community edition, and so I just use the professional version, which is much faster. All right, so the first thing you do when you're testing for cross-site scripting vulnerabilities is you look for client-supplied input that is reflected back in the application. So in the search functionality over here, I'm going to add the keyword test, click on search, and as you can see over here, my client-supplied input is being reflected back in the application, and so this field definitely needs to be tested for cross-site scripting vulnerabilities. What I'll do first is test it for a really obvious and classic case. So I'll say script, alert 1, and then end the script tag, and click on search over here and see if the application accepts it. So I get a custom error, likely from a web application firewall, that says this tag is not allowed. So now what I'm going to do is try to see if there are tags that are allowed that it could potentially allow me to perform my cross-site scripting attack. So to do that, let's search on just script itself, click on search, intercept the request in Burp, and then let's send this to intruder. So what we're going to do is we're going to get all the possible tags, and then we're going to automate the process of figuring out which tags are allowed and which ones are not. So let's clear over here. The less than and bigger than signs don't actually need to be URL encoded, so I'm just going to rewrite this over here. And the part that we want to automate is this one over here. So this is the field where we're going to enter a bunch of tags and see which ones work. If I get this message over here, that means that tag is not allowed. However, if I get a 200 OK message, that means that tag is allowed. So to get the list of tags, I'm going to Google XSS cheat sheet portswigger, hit enter, and on the first entry over here, you get a really useful resource for cross-site scripting that gives you the list of all tags and then all the events and then for which browser. And once you put your selection over here, it actually gives you the option. It tells you what it does, and then it gives you the payload that you could use. So this is a really useful resource that we're going to use when we're trying to bypass web application firewalls. The first thing I'm going to do is figure out which tag is allowed. So let's copy tags to clipboard. And then in payloads, paste it in here and run our attack. So in the community edition, again, this works. It's just going to be much slower than in the professional version. So let's go on status right over here. You see that there's a bunch of tags that are allowed, which is quite odd because the name of the lab is all tags are blocked except the custom ones. So I'm just going to go over here and see if it's all done correctly and see the response and render it. And interesting. So there might be something wrong with the lab that is preventing all these tags. However, when that gets fixed, I don't want to provide you with the wrong solution. So let's assume that all the tags were blocked except for custom tags. So in this case, we're going to try and solve the solution with a custom tag. So let's close this off, discard, and go back to our cheat sheet and select custom tags. And we want it for, let's say, the Chrome browser. And here we go. So you're presented with a bunch of options for custom tags. And now the next step is just to select a payload that could potentially work on the application. So over here, this fires when a CSS animation ends. I don't really like that. This one is when a CSS animation starts. This one fires when the element has focus. So let's try this one out. Let's copy it, put it in here. And then instead of alerting over here, I'm just going to say console document.log and just print the message hello in the web console. So we'll know it worked if we get the message hello in the web console. So let's click on search over here. So far so good. Let's inspect and go to our console over here, and here we go. So we get the message hello, which means that the exploit worked. So now we need to deliver this exploit to the victim user, and the way we're going to do that is by using our exploit server, which is just our attacker controlled server. So we'll go over here, we'll add a script tag. So in a real world scenario, this application would look like a legitimate application. And so the user would be visiting the application, and what's really happening when the user visits the application is they essentially run this XSS code in their browser, and then they would send the document.cookie, so the cookie that is saved in the browser, to the attacker. So for now, we just need to alert on it. So let's say script location is equal to our payload. So if we go to proxy right over here, it was this one right over here. Let's copy it. First, we need our URL of the application. Let's put it in here. And then copy the XSS payload. This looks good. So essentially over here, we were just printing to console.log. What we want to do is actually alert on document.cookie. So before we send this to the victim user, let's send this to repeater and build our exploit. So over here, this is URL encoded. I'm going to do Control-Shift-U to decode it. And then instead of console.log, I'm going to say alert on document.cookie. And that's pretty much it. So let's URL encode this, copy it, paste it in here. And we actually don't want to URL encode this part over here. That might break it for us. So let's URL decode it again. And we only want to URL encode this part over here. So Control U again to URL encode it. And here we go. I believe we got it right this time around. All right. Let's paste it in here. And we need the link to the application itself. So we'll add HTTPS. And then the link to the application. And this looks good. Hopefully this should work. Now this is all in the location variable, so we need to put it in double quotes. And let's copy this, put it in notes.txt, and I'll provide you the link to the document in the description. And then let's deliver the exploit to the victim. And we don't get the congratulations, you solved the lab message, which means that there is something wrong with our exploit. So let's view the exploit. You could see over here, we're not seeing anything. Let's inspect and then go to the console, and here we go. So we're getting an error on HTTPS, which means that there must be some kind of error in our code. So let's go back. Let's minimize this. This all looks okay to me. Let's add a semicolon over here. And let's put this in single quotes. Oh, and I understand what happened. So I had put 2 single quotes instead of a double quote, and I assumed that I put a double quote, and that's why it wasn't working. All right, let's view the exploit. And we get alerted. We don't actually have a cookie for this application, and that's why we're alerted with nothing. But if we close this off and then go back to the exploit server and deliver this to the victim user, but before we do that, let's update this over here and save it, and then deliver the exploit to the victim user, you should see the congratulations, you solved the lab message. All right, so we successfully completed the exercise by exploiting the reflected XSS vulnerability. In the next lab, we'll look at another case of a cross-site scripting vulnerability. Hi everyone, welcome back to another video in the Web Security Academy series. In today's video, we'll be covering lab number 19 in the cross-site scripting module titled Reflected XSS with some SVG Markup Allowed. If you do not have an account on the Web Security Academy, you can get one by visiting the URL portsfigure.net/websecurity and clicking on the sign up button. I already have an account and I am logged in, so to access the exercise, I'm going to click on Academy, select all labs, do a search and lab number 19 titled Reflected XSS with some SVG markup allowed. Let's select the lab. All right, let's get started. This lab has a simple reflected cross-site scripting vulnerability. The site is blocking common tags but misses some SVG tags and events. To solve the lab, perform a cross-site scripting attack that calls the alert function. All right, so the target goal over here is to perform a cross-site scripting vulnerability that calls the alert function. Let's access the lab. Now notice over here, this is the built-in browser in Burp, and so all my requests are already being passed in my Burp proxy. Now, when I'm searching for cross-site scripting vulnerabilities, the first thing that I look for is input fields that are reflected back in the application. So I'm looking for client-supplied input like this search field right over here, where if I put in a string, let's say test, and I click on search, my input is reflected back in the application. So you could see over here, it is reflected back to me in the browser. And so this definitely needs to be tested for reflected cross-site scripting vulnerabilities. And we'll start off with a really simple test. So let's say script alert 1 and close off the script. All this does is essentially create a window or pop up a window that has the integer 1 in it. So let's click on search. And the application is a little bit slow, but you could see over here it says tag is not allowed. So this is interesting. It means that there is some kind of firewall or some kind of validation in the backend code that is checking for certain tags. And if it sees that you're using a certain tag, it says, well, maybe this person is trying to attack the application and it prevents you from performing the request. So what we're going to do is right click on the request that we just performed and send it to intruder. Now, the reason we're doing that is because the script tag is not the only one that we can use in order to perform a cross-site scripting attack. And so we're going to test all the different possible tags. Let's remove all of this and just keep the script tag over here. So this is just the less than and the bigger than sign. And we'll add this as the variable that we want to enumerate. Now, in payloads right over here, we're going to add our list. And we get that by just Googling XSS cheat sheet Portswigger. So Portswigger has a really nice cheat sheet that contains all the different tags and all the different events that could potentially be used in order to perform cross-site scripting attacks. And it's updated very frequently. So you could see over here, today we're in June. However, this was updated just last month, so in March. So let's copy this tag over here, our list of tags, and paste them. Now, I am using the professional version of Burp because I do want my attack to go quickly for the video. However, if you're using just the free version, it will still work. It just will be heavily throttled. So the attack is going to take a little bit longer to perform than if you were to use the professional version. If you want it even faster, you could just write a Python script that tests each individual tag, and the one that doesn't give you, I believe, a 400 error message. So if we go back to proxy, and it was a 400 error code. So the request that doesn't give you a 400 error code, that means the tag is allowed. So let's go back to intruder over here and click on start attack. And this is just going to take a couple of seconds. All right, it looks like it's going to complete soon. Now what we're looking for is, again, an error code that is different from a 400 error code. So we're likely looking for a 200 status code. So let's click on status right over here. And here we go. So we can use animate transform, we can use image, we can use SVG, and we can use title. All of these work. So if we go down right over here and look at the different payloads that we could use. So let's go down and look for SVG. So you could see over here, you've got the option SVG, you've got the option SVG with animate, and then SVG with animate motion. SVG with animate transform, and SVG with set. So I could see over here both SVG and the animate transform tags are allowed. So I'm just going to select this one because it's likely to be the one that will most likely work. So if we go down right over here, you could see there are 3 different ways that you could potentially perform a cross-site scripting attack. So the first one over here, it fires when an SVG animation begins. The second one fires when an SVG animation ends, and then the third one fires when an SVG animation repeats. So all 3 of them are likely going to work, so I'll just copy the first one and go back to the lab over here and paste it in our field. All this does is essentially when the SVG, again over here, it says when the SVG is fired up, all it does is it runs this JavaScript, and all the JavaScript does is alert on the number 1. So click on search, and here we go. Click on OK, and we should see the congratulations, you solved the lab message. All right, so we successfully completed the exercise by exploiting the cross-site scripting vulnerability. In the next lab, we'll look at another case of an XSS vulnerability. Hi everyone, welcome back to another video in the Web Security Academy series. In today's video, we'll be covering lab number 20 in the cross-site scripting module titled Reflected XSS in Canonical Link Tag. If you do not have an account on the Web Security Academy, you can get one by visiting the URL portswigger.net/websecurity and clicking on the sign up button. I already have an account and I am logged in, so to access the exercise, I'm going to click on Academy, select all labs, do a search on cross-site scripting labs, and go down to lab number 20, titled Reflected XSS in Canonical Link Tag. Alright, let's get started. This lab reflects user input in a canonical link tag and escapes angle brackets. To solve the lab, perform a cross-site scripting attack on the home page that injects an attribute that calls the alert function. To assist with your exploit, you can assume that the simulated user will press the following key combinations. So you've got Alt-Shift-X, Control-Alt-X, and then Alt-X. And then we've got a note here saying, please note that the intended solution to this lab is only possible in Chrome. All right, so we need to perform a cross-site scripting attack that when a user performs one of these key combinations, it calls the alert function. Let's access the lab. Now notice over here, this is the built-in browser in Burp, and so all my requests are already being passed in my Burp proxy. However, all the features that I use are present in the Community Edition, and so you could just complete the lab with the Community Edition. Okay, so the first thing we're going to assume over here is that you've tested the application and you can't find any parameters that are reflected back to you in the application and are vulnerable to XSS. In that case, the next step is to see if the URL accepts a random parameter. And the way to do that is just to put in a question mark, so a slash and then question mark, and then just say random is equal to test and see if the application accepts that. So let's hit send. The application is still loading fine. Now let's view the page source to see if there's any reflection for this parameter that we just added. So let's do control find and then look for test. And it looks like there is one reflection over here. So hit send and here we go. So the reflection is in a canonical link, which is interesting. Now, since we do have a reflection, we're going to try to see if it's vulnerable to a cross-site scripting vulnerability. So let's copy that and put it in here. Let's remove this space and remove the title line. Now the idea over here is to perform a cross-site scripting attack. So the first thing that I'm going to do is see if I could add an attribute called onClick that alerts on a random string. So to do that, we're going to add a single quote so that we could close off this string right over here, and then a space and say onClick is equal to single quote, and then alert 1. And then this single quote over here will be closed off with a single quote that is present in the application itself. So let's copy that and see how it gets displayed in the code. So if we go back right over here and remove the previous string that we inputted, and put the new one and let it load. Interesting. So we can add the onClick attribute. However, notice over here that we get a %20, which is just the URL encoded version of a space sign. This is not a good sign because I do need a space over here. So I'm going to try to find another way of entering a space. And one way to do that is just to add the URL encoded version of a tab sign. So let's say tab URL encode and visit the W3 schools link and do a search on tab. Here we go. So for a horizontal tab, it's %90. So let's try that. If it doesn't work, we'll try vertical tab. So instead of the space over here, you would put %90, and let's see how the application responds. So let's copy our exploit string again, close this off, and add it in the application. Let's remove it from over here and add the new one. And we have 2 backslashes, so let's remove that backslash and hit enter. And let's view how it's displayed in the code. Okay, perfect. So you could see over here now I do have a space, so the tab works, and my onClick element is being viewed as code. Perfect. So right now I am running into one issue, which is that this link over here is not actually displayed on the page. And so I need a way to trigger this element over here so that I could execute the alert function. And that's why over here they said to assist with your exploit, you can assume that the simulated user will press the following key combinations. And so when the user presses Alt-Shift-X or Control-Alt-X or Alt-X, what'll happen is I needed to trigger this alert function right over here. And to do that, I'm going to add something called an access key, which is simply just an attribute that provides a keyboard shortcut for an element. So to do that, we'll just close this off one more time and then say access key is equal to. And over here, this could be anything, but because the user, so the victim user over here will be clicking on X, you do have to put X in here. Had this said W or Z or whatnot, you would have to put in the character that is added in the lab description. So in this case, it's X, and so we'll keep it that way. And that's pretty much it. Now notice over here, there is a space sign, and that's not going to work. So let's add the tab URL encoded version. All right, let's copy our new exploit. Hopefully this will work. And let's go to view source over here. Remove the previous exploit. And add it in here. And if we go to the right, you could see over here my access key attribute was added correctly, and I still have my onClick attribute. So now if we go to the lab, so let's remove view source right over here and hit enter. It should say, congratulations, you solved the lab. And the reason it did that is because the simulated victim user performed one of these key combinations and was alerted with the alert message. All right, so we successfully completed the exercise by exploiting the reflected XSS vulnerability. In the next lab, we'll look at another case of a cross-site scripting vulnerability. Hi everyone, welcome back to another video in the Web Security Academy series. In today's video, we'll be covering lab number 21 in the cross-site scripting module titled Reflected XSS into a JavaScript string with single quote and \escaped. If you do not have an account on the Web Security Academy, you can get one by visiting the URL portswigger.net/websecurity and clicking on the sign up button. I already have an account and I am logged in, so to access the exercise, I'm going to click on Academy. Select all labs, do a search on cross-site scripting labs, and go to lab number 21, titled Reflected XSS into a JavaScript string with single quote and \escaped. All right, let's get started. This lab contains a reflected cross-site scripting vulnerability in the search query tracking functionality. The reflection occurs inside a JavaScript string with single quotes and \escaped. To solve this lab, perform a cross-site scripting attack that breaks out of the JavaScript string and calls the alert function. All right, so our target goal over here is to perform an XSS attack that calls the alert function. Let's access the lab. Now notice over here, this is the built-in browser in Burp, and so all my requests are already being passed in my Burp proxy. I am using the professional version of Burp. However, to complete the lab, you could perform everything that I'm performing just in the browser or in the community edition of Burp. All right, so as usual, the first thing that I do when I'm looking for cross-site scripting vulnerabilities is I look for client-supplied input that is reflected back in the application. So in the search functionality over here, I'm going to add a random string, hit search, and notice that there is reflected input. We need to confirm that this is the only instance of reflected input. So I'm going to right click and view page source and do a search on test. Now notice over here, there are two places where the input is reflected. The first one is the heading, which we saw on the page. And then the second one is in the script tag. So this is interesting. Now, both these places need to be tested for cross-site scripting vulnerabilities. What I'm going to do first is see if the application allows the script tag. So click search. And if we view the page source right over here, you could see that in the heading element, the less than and greater than sign are URL encoded. However, in the script tag, they're not URL encoded. And so right now, my target is going to be the script tag instead of the heading tag, because likely the heading tag does have proper URL encoding. So for this one over here, you could see it's in a string for the variable search terms. So the first thing I'm going to try is to break out of that string using a single quote. So let's do that directly in the URL. Let's just say single quote, hit enter. Let's go down, and you could see over here that single quote is being escaped. So I might not be able to use the single quote. The next thing that I'm going to try to do is just immediately break out of the script tag itself. So let's do that. So let's remove this over here and just say /script, hit enter, and see how it's interpreted. So if we go down over here, you could see that it's interpreted as code. So this is a really good sign. That means I've broken out of the script tag, and now I could just add my own exploit, and it'll be a really simple one. So this was us breaking out of the script tag, and now we could just add a new script saying alert1 and close off our script. And this should work. So let's copy this, paste it in here, click on search, and we get presented with the alert functionality. Click on OK, and we get the congratulations, you solved the lab message. All right, so we successfully completed the exercise by exploiting the reflected XSS vulnerability. In the next lab, we'll look at another case of a cross-site scripting vulnerability. Hi everyone, welcome back to another video in the Web Security Academy series. In today's video, we'll be covering lab number 22 in the cross-site scripting module titled Reflected XSS into a JavaScript String with angle brackets and double quotes HTML encoded and single quotes escape. If you do not have an account on the Web Security Academy, you can get one by visiting the URL portswigger.net/websecurity and clicking on the sign up button. I already have an account and I am logged in, so to access the exercise, I'm going to click on Academy, select all labs, do a search on cross-site scripting labs, and go down to lab number 22, titled Reflected XSS into a JavaScript String with angle brackets and double quotes HTML encoded and single quotes escaped. All right, let's get started. This lab contains a reflected cross-site scripting vulnerability in the search query tracking functionality where angle brackets and double are HTML encoded and single quotes are escaped. To solve this lab, perform a cross-site scripting attack that breaks out of the JavaScript string and calls the alert function. All right, so our target goal over here is to perform an XSS attack that calls the alert function. Let's access the lab. Now notice over here, this is the built-in browser in Burp, and so all my requests are already being passed to my Burp proxy. All right, as usual, the first thing you do when you're testing for cross-site scripting vulnerabilities is you look for client-side parameters that get reflected back in the application. So for example, over here, if we say test and click on search, you could see over here that my input was definitely reflected back in the client-side code of the application. Let's right-click and view page source to see if there's any other part in the application where it's reflected. So let's do Control Find and look for the string test. You could see over here there are two entries. The first one is in the heading parameter, which we saw right over here. And then there's a second one, which is not directly visible to us in the browser, that is in a script. So you can see over here, we've got a variable called search terms, and then the value that we put in here gets inputted in here, and then the application does some kind of writing to the page with that. All right, so both fields definitely need to be tested for cross-site scripting vulnerabilities. The first thing that I'm going to do is add a bunch of characters that are used when we're testing for cross-site scripting and see if these characters are being encoded. So if we go back over here, let's do less than sign and then test, and then let's do single quote and double quote and see which characters are being encoded. So let's hit search right over here and then view the page source. And if we go down over here, you could see in the heading parameter, the less than sign, the single quote, and the double quote are all URL encoded. But over here in the script tag, the less than sign is URL encoded, the double quote is URL encoded, but the single quote is only escaped. So that's interesting. Maybe we could try and exploit that. So what we're going to do over here is go back to our payload. So we've got the search field right over here. And then let's just remove everything except for a backslash and a single quote. So what I'm trying to do over here is see if the backslash itself is escaped. If it's not, when I put a backslash right over here, what it'll do is it'll escape this backslash and then my quote is no longer escaped. So let's hit enter. Go down, and here we go. So you can see this is my backslash right over here. This backslash escapes it, and then my single quote right now is valid and is no longer escaped. So this is really good. Now the next step is just simply to add my alert function because I got out of this string right over here. So to do that, let's go to our text document and just add a regular string that will be inputted in the search field right over here. And then we've got our backslash and single quote. And then I'm going to add a semicolon to end this variable right over here. And then I just add alert 1 and then semicolon. And then we're left with a single quote and a semicolon. So we could just use the slash sign, so the double slash sign, in order to comment it out. So let's copy this, put it in here, and close this off and click on search. And here we go, we're presented with the alert function. Click OK, and you should see the congratulations, you solved the lab message. Now, if we view the source code, you could see over here, essentially what I did is I just closed off this search term over here. I added my alert function, and then I just commented out the rest of the characters that were available in the script. And that is pretty much it. So we successfully completed the exercise by exploiting the reflected cross-site scripting vulnerability. In the next lab, we'll look at another case of a cross-site scripting vulnerability. Hi everyone, welcome back to another video in the Web Security Academy series. In today's video, we'll be covering lab number 23 in the cross-site scripting module titled Stored XSS into OnClick Event with angle brackets and double quotes, HTML encoded in single quotes and backslash escape. If you do not have an account on the Web Security Academy, you can get one by visiting the URL portswigger.net/websecurity and clicking on the sign up button. I already have an account and I am logged in, so to access the exercise, I'm going to click on Academy, select all labs, do a search on cross-site scripting labs, and go down to lab number 23, titled Stored XSS into OnClick Event with angle brackets and double quotes, HTML encoded, and single quotes and backslash escaped. All right, let's get started. This lab contains a stored cross-site scripting vulnerability in the comment functionality. To solve the lab, submit a comment that calls the alert function when the comment author name is clicked. So our target goal over here is to perform an XSS attack that calls the alert function when the comment author name is clicked. So let's access the lab. Now notice over here, this is the built-in browser in Burp, and so all my requests are already being passed in my Burp proxy. All right, as usual, when you're looking for cross-site scripting vulnerabilities, you're looking for client-supplied input that gets reflected back in the application. So if you go down right over here and click on View Posts for one of the posts, you could see that there is a comment functionality and you're allowed to leave comments. So any comments that you enter over here will get displayed back to you in the application. And so any fields that get displayed should be tested for cross-site scripting vulnerabilities. The first thing we're going to do is put in dummy data and see which fields are displayed to us. So for email, let's say test@test.ca, and for website, let's say http www.test.ca, and post a comment. Let's go back to the blog. And when we do that, let's actually just send our post request to repeater just in case. And if we go down right over here, you could see this is our comment. So the comment field is reflected back to us. The name field is reflected back to us. And if you hover over the name field, the website field is also reflected back to us. So all three should be tested for cross-site scripting vulnerabilities. I'm just going to right click and inspect and do that again so that it works. And I accidentally clicked on it, so it's trying to visit test.ca, which doesn't really exist. So let's go back to the blog, go down, and then right click and inspect. And here we go. So you could see right over here, we've got the name of the author in the A element. We also have the website in an href attribute and in an onClick attribute. So it gets placed in two locations. Now, based on the exercise description, it says perform an XSS attack that calls the alert function when the comment author name is clicked. And so we need to exploit the XSS vulnerability within the onClick function. So our exploit should be in here so that when a user clicks on the user's name, the XSS vulnerability gets run. So let's right click and view page source and look for test at test.ca. This is the string that we want to exploit. So let's copy it, put it in here. And we're specifically looking for onClick. So let's remove all of this because I don't really care about it. All right, so we need to somehow inject our cross-site scripting vulnerability in this function right over here for the user to be able to click on a name and then for this cross-site scripting vulnerability to execute. So what I'm going to do over here is go back to the application and just see if the application accepts any random website. So let's say test, and then test.test.ca. And then for the website, let's say http www.test.ca, and then let's say script, hit enter. And it looks like it accepted it, which is a little bit shocking. So if we go back over here and we hover over this, you could see, oh, it URL encoded it, and that's why. So let's build our payload first and see if the application will accept it. And if it's not, we'll have to just alter our payload to one that is accepted by the application. So the first thing that we need to do is close off this string right over here. And so I'm going to add a single quote, and then I'm going to add my alert function. So we'll use the minus sign, alert, one, and then minus sign again. And then we need to close off this single quote. So we'll add another single quote right over here. So let's copy this and see how the application interacts with it. So let's say test, and then test at test.ca. And then for this one over here, we add our payload, post comment. Go back to the blog, go down, and let's inspect this. Go down, and it looks like the single quote is escaped. So that's going to be problematic. The next thing I'm going to do is try and see if the HTML entity version of a single quote is escaped. So that would be and a pause and then semicolon. So let's replace our single quotes with that. So that would be one, and this would be another one. Let's copy this entire thing and add another comment. And then let's say test out. Oh, this would be our field for the exploit, post comment. And here we go. It says, congratulations, you solved the lab. Let's go back to the blog over here. Go down and just click on it to see if we're alerted. And we are alerted. Let's click OK. And then we get an invalid client request because we're trying to access a URL that does not actually exist and is not really invalid. All right, so the payload that worked for us over here was this one over here. I'll leave the link to the notes.txt document in the description. Okay, so we successfully completed the exercise by exploiting the stored XSS vulnerability. In the next lab, we'll look at another case of a cross-site scripting vulnerability. Hi everyone, welcome back to another video in the Web Security Academy series. In today's video, we'll be covering lab number 24 in the cross-site scripting module titled Reflected XSS into a Template Literal with angle brackets, single, double quotes, backslash, and backticks Unicode Escape. If you do not have an account on the Web Security Academy, you can get one by visiting the URL portswigger.net/websecurity and clicking on the sign up button. I already have an account and I am logged in, so to access the exercise, I'm going to click on Academy, select all labs, do a search on cross-site scripting labs, and go down to lab number 24, titled Reflected XSS into a Template Literal with angle brackets, single, double quotes, backslash, and backticks Unicode Escaped. All right, let's get started. This lab contains a reflected cross-site scripting vulnerability in the search block functionality. The reflection occurs inside a template string with angle brackets, single, and double quotes HTML encoded and backticks escape. To solve the lab, perform a cross-site scripting attack that calls the alert function inside the template string. All right, so the target goal over here is to exploit the reflected XSS vulnerability and call the alert function. Let's access the lab. Now notice over here, this is the built-in browser in Burp, and so all my requests are already being passed in my Burp proxy. All right, as usual, when it comes to cross-site scripting vulnerabilities, what you want to do is look for input that is taken from the client side and reflected back in the application. So if we put a string right over here and click on search, you could see that in the output, the string that we put in the search field is reflected back to us in the application. Now let's see if there's any other places that are not directly visible to us in the browser. So right click and view page source and look for the string test. Now you could see there's only one instance of it, and it's the one in the heading field that we saw right over here. But the interesting thing over here is you could see that the string is in a variable called message, and the way the variable is set is using backticks. Now, this immediately tells me that they're using the JavaScript template engine because of the backticks. And the thing with that is you could execute client-side code in a template engine. All you have to do is really use the syntax to execute a function. And the syntax would be just the $, and then whatever function you want to execute. So we want to alert on something, and we'll just alert on the number 1. So let's copy this, put it in here. Since it is being executed in a template engine right over here, we should be presented with the alert function. So let's click search. And here we go. We are presented with the alert function. Click on OK, and you should see the congratulations, you solved the lab message. All right, so we successfully completed the exercise by exploiting the reflected XSS vulnerability. In the next lab, we'll look at another case of a cross-site scripting vulnerability. Okay, let's get started with the first section, which is what is a cross-site scripting vulnerability. Cross-site scripting, or in short XSS, is a vulnerability that allows an attacker to inject malicious code or client-side scripts in the application that ends up getting executed in the web browser of the victim user. So unlike SQL injection or command injection, cross-site scripting is a client-side vulnerability. When you exploit this type of vulnerability, you're not actually exploiting the application server. You're exploiting the users of the application. Let's take an example to better understand this. Imagine you have a banking application that allows you to choose the language of your preference. So you're given the option of either English or French. Now, when you select the language, what happens is that the application performs a request that takes in your language preference as input to a parameter in the URL. It changes the language, and your input gets reflected back in the client-side code. Now, this makes it a perfect recipe for cross-site scripting vulnerabilities. As an attacker, what I could do is visit the application and inject my malicious code in the language parameter. Now, since this gets reflected back in the source code of the application, then if there's no validation on this lang parameter, I could inject whatever code I want. So if you look over here at the example, the first thing that the attacker did is look at the application to see if there are any parameters in the application that accept client-supplied input, and that client-supplied input gets reflected back in the source code of the application. So it gets reflected back in the browser. And the attacker finds out that the lang parameter, which should really just have either English, so EN for English, or FR for French, the lang parameter was found to actually accept any string of characters. And so what the attacker does is that he constructs a malicious script, and then he hosts that malicious script on his server, so attackerserver.net, and then uses the vulnerable parameter to call that script and execute it in the banking application itself. Now, the issue over here is that if the attacker clicks on this link right over here, the attacker is executing the script in his own browser. So essentially, the attacker is exploiting himself. So with this type of cross-site scripting vulnerability, which is also known as reflected cross-site scripting, you need to phish the user, or you need to get the user to click on the link that contains the malicious code so that the malicious code runs in the browser of the victim user. So if we go back to our example over here, after the attacker has identified the vulnerable parameter and injected his malicious script in the vulnerable parameter, the attacker has to entice the victim user, which is Alice in this example, to click on the link. Now, when Alice receives the email that says, hey, you could perform your banking applications using this link over here, Alice is not stupid. She's gone through all the security trainings, and she knows that she needs to check the domain of the link. Now, Alice hovers over the link and sees that the domain is truly the domain of her banking application, which means that she should trust the link and click on the link to perform her banking operations. And that's essentially what she does. She clicks on the link, she gets directed to her legitimate banking website, and she performs all the banking application that she needs to perform. However, what's happening in the background is that this script right over here, so the malicious script, ends up executing in Alice's browser. It accesses Alice's cookie store for this application, steals Alice's session token, and sends it to the victim user. And that's essentially how cross-site scripting vulnerabilities work. The idea is you're injecting client-supplied input in the application that ends up getting run in the victim's browser, and then potentially performing actions on the behalf of the victim, or even in worst-case scenarios, compromising the victim's account. Now you might be thinking, this is such a long process. Why even exploit the cross-site scripting vulnerability? The attacker could just direct the user to the attacker-owned server, and when the user clicks on the link, it'll execute in the user's browser and steal all the user's session tokens, not just the session of the banking application. Well, that's not exactly how it works. Browsers abide by a rule called the Same Origin Policy, or in short, SOP. This policy segregates content that is received from different origins or domains to prevent different domains from interfering with each other in the user's browser. So the browser does not let any random script that is running on a different domain from accessing the content and the responses of the application. The request has to be originating from the application itself, which is why for this attack to work, you absolutely need to be able to inject your malicious code in the application itself, just like we did over here. The malicious script is truly running on the legitimate application bank.com, and that's why it's able to access the content of the browser for this application and compromise the user's account. All right, hopefully we now have a proper understanding of how cross-site scripting vulnerabilities work. Let's move on to discuss the different types of cross-site scripting. There are three different types of cross-site scripting vulnerabilities. The first one is reflected XSS. The example that we saw was a type of reflected cross-site scripting vulnerability because the user's input was directly reflected back in the response of the request. Now, there are two other types of cross-site scripting vulnerabilities. The first one is stored XSS, and the second one is DOM-based XSS. Stored XSS is really similar to reflected XSS with the exception that the malicious code gets stored in the application instead of directly reflected back in the response. This type of XSS is way more dangerous because you no longer need a phishing component to your attack. Let's take an example to better understand this. Imagine you have an application that allows you to post your review on products that you bought, and this review becomes available to everyone else that visits the page for that specific product. In this case, if the input is not validated in the backend, then the attacker could simply inject his malicious script in the comment field, post the comment, and this way anyone that visits the page, the malicious script ends up getting executed in their browser. So not only does stored XSS no longer require you to deliver the exploit to the victim user through a phishing link, but now you can also compromise a ton of users. Anyone that visits the page can be compromised. Now, there's a ton of stored XSS vulnerabilities that have been found in real-world applications, but a really famous example is the MySpace social networking site. In 2005, it was found to be vulnerable to a stored XSS vulnerability in the user profile page. So a user, or also an attacker called Sammy, he placed malicious JavaScript in his profile page so that anyone who visits his profile, the script executes, it adds Sammy as a friend, and it copies the content of the script in the victim user's profile page. This way, when anyone also visits the victim user's profile page, Sammy gets added as a friend, and then the malicious script gets also added in the other victim's user's profile page. This was essentially an XSS worm that spread across the entire social networking site to the point that MySpace had to be taken offline and they had to remove all the malicious scripts from all the victim users' profiles. So this is definitely something that you should look for. All right, that was stored cross-site scripting vulnerabilities. Let's move on to DOM-based cross-site scripting vulnerabilities. DOM-based XSS is a type of cross-site scripting attack where the attack payload is executed as a result of modifying the DOM environment of the victim user. For those of you that are not familiar with the DOM, DOM stands for Document Object Model, and it's essentially the programming interface or API for HTML and XML documents. The way it works is when you load a web page into the browser takes the HTML of the application and converts it to the DOM, and then any JavaScript in the application can access the DOM to dynamically change elements within the HTML document. Now, DOM-based XSS vulnerabilities, as the name suggests, occur when the JavaScript is taking in client-supplied input and passing it to what we call a sink, or a potentially dangerous function without any validation. To better understand how this works, let's go back to reflected cross-site scripting vulnerabilities and then compare them to DOM-based cross-site scripting vulnerabilities. In this example over here, the vulnerable request is a GET request, and it takes in a parameter message. Now, this parameter contains the message that you want to display to the user, and in this case, the message is all is well. So the content of the message parameter is inputted in a paragraph element in the HTML document and displayed to the user. This is the view that you would see if you right-click in your browser and then click on View Page Source. Now, if this message field has no validation whatsoever, then an attacker could simply inject a malicious script that alerts on the cookie of the user. Anything that you put in the message field gets added in the HTML paragraph element, and when the HTML document is rendered, the browser sees that this is a paragraph element and it contains the status string, and so it displays status to you as the user. However, when it gets to the script element over here, it sees that this is JavaScript, and so it essentially treats it as JS code, and it calls the alert function, and then in the alert function, it displays the content of the cookie of the application. So for you as a user, you'll see an application that contains the string status, but you'll also be alerted with a window that contains the content of your application cookie. And that's essentially how reflected cross-site scripting vulnerabilities work. Now, the key thing to understand over here is that the XSS payload was directly inserted in the HTML page itself and changed the content of the page. DOM-based XSS vulnerabilities work a little bit different. The page itself does not change, but the client-side code contained in the page executes differently based on the malicious input that you give it. In this example on the screen, you have a search functionality that allows you to search for items in an online store. Now, when you enter your input, it does not get directly reflected in the page, just like with reflected cross-site scripting. Instead, the application uses some JavaScript to read the value of the search field and then write the value to an element within the HTML document. Here, our sink would be the inner HTML property because it alters the content of the HTML page. And so if there's no validation on the client-supplied input, then it could potentially be vulnerable. The exploit would involve adding an image tag that when there's an error in loading it, it executes your malicious function. Now you might be thinking, why not use the script tag that we did in the previous example? And the answer is that according to the HTML5 specification, the script tag won't execute within the inner HTML property, so we had to get a little bit creative and use the image tag. But the takeaway over here is that DOM-based XSS attacks involve modifying the DOM environment of the victim user versus your input just getting reflected back in the page and modifying the HTML page itself, which is why they're a little bit more difficult to find and exploit. We'll look at more examples when we discuss how to find and exploit these types of vulnerabilities. Alright, now that we have discussed the three different types of XSS vulnerabilities, let's talk about what you as an attacker can do when you identify that the application you're testing contains a cross-site scripting vulnerability. The first thing that you could do, and it's the first thing that most attackers would do, is see if they could impersonate or masquerade as the victim user. This attack vector usually involves stealing the session token of the user. Now, this is only possible if the session token is stored in an insecurely configured cookie, so a cookie that does not have the HTTP-only flag set, or the session token is stored in insecure locations that are accessible by JavaScript, like local storage or session storage. Another thing you could do is carry out any action that the user is able to perform and read any data that the user is able to access. Since your malicious code is running in the application in the user's browser, you're essentially able to perform any action that the user can perform in the application. You could also inject Trojan functionality into the application that models the login functionality of the application and tricks the user into inputting their credentials. To make the attack even more sophisticated, you could actually relay the credentials in the fake login functionality to the real login functionality so that the user logs into the application and doesn't understand that there's an attack that is happening. But what happens in the background is that you send the login credentials of the user to your attacker controlled server and essentially compromise the user's account. You could also deface the application with inappropriate or politically motivated messages. So this is just a sample list of attack vectors that you can perform with XSS vulnerabilities. There's really an endless list of possibilities, which brings us to our next slide, covering the impact of XSS vulnerabilities. The impact of an XSS vulnerability largely depends on the type of XSS vulnerability that you identify in an application and the attack vector that you want to perform, so your goals and motives. We saw an example where an attacker wants to deface a website. In that case, integrity is heavily impacted. However, confidentiality and availability are not impacted. Now, in other cases where, let's say, you perform a full account compromise, it could impact all three: confidentiality, integrity, and availability. In fact, what attackers usually do is chain the XSS vulnerability with other vulnerabilities in the application to achieve a full account takeover or even remote code execution. A real-world example of that is the Magento application. Last year, it was found to have a critical vulnerability that involved exploiting a stored XSS vulnerability that can eventually lead to an arbitrary code execution, which tells us that when you chain the XSS vulnerability with other vulnerabilities in the application, or other functionality in the application that is usually only available to highly privileged users, it can have disastrous consequences. And that's why XSS now falls under the third most critical security risk facing web applications today. It used to have its own category in 2010, in 2013, and in 2017. However, right now it got looped into the injection category, which is the third most critical security risk facing web applications today. I've personally tested a ton of applications and I'm yet to find one application that does not have a cross-site scripting vulnerability in it. So these types of vulnerabilities are definitely still around and can lead to terrible consequences.